Across most of the cosmos, the laws of physics run the show. Stars fuse hydrogen, planets trace orbits, galaxies spin on cosmic timescales. But scattered across space are places so extreme, so alien, that the rules break down completely. Gravity folds time into knots, matter melts into exotic forms beyond any laboratory experiment, and space-time itself flickers like static on a dying screen. These aren't just curiosities, they're the frontiers where our equations fail, where reality itself slips beyond the reach of known science. Event horizons of black holes. Black holes are known to be very strange. They can hold things so tightly that not even light can escape. But the event horizon is where physical understanding ends. It's the unseen edge around a black hole where the speed of light is the escape speed and space and time are warped so much that the words inside and outside have lost their normal meanings. If you go past this limit, no signal, particle, or photon will ever come back. It's the only way out of the world that can be seen, and this is where science starts to wobble under the extreme pressure. The event horizon looks very easy when you look at the numbers. According to general relativity, space-time is like a smooth, flexible cloth that is shaped by energy and mass. For a Schwarzschild black hole, which is not spinning and is not charged, the event horizon is at the Schwarzschild radius, which is equal to the mass of the object. If you double the mass, you get twice the radius. A black hole with the mass of the Sun would only have a horizon that is 3 kilometers wide, but the one in the middle of our galaxy is 25 million kilometers wide. But the event horizon always acts the same way. If you cross it, you can't get away because space-time moves inward faster than light can move outward. At the horizon, you shouldn't have any strange things happen to you. Einstein's equality principle says that people who are falling through space don't feel any gravity. If you cross the event horizon of a giant black hole, you might not even notice the time. There is still light from faraway stars, your tools are still working, and your spaceship doesn't feel any bumps. Physics seems normal in this area. However, your fate is set on a global scale. Going forward in time now leads inward toward the singularity, which you can't avoid. For distant observers, the story looks very different. As you approach the horizon, signals you send outward take longer to arrive, redshifted to lower and lower energies. To someone watching from far away, you never actually cross the horizon at all. You freeze, dimming toward blackness as time appears to stop. This is not an illusion, but relativity itself. Time and space trade roles near the horizon, with moving inward becoming as inevitable as moving into the future. Once you cross, outward no longer exists as a direction through space. Only inward, and the unstoppable flow of time toward the center remains. The event horizon also forces a collision between two great theories, general relativity and quantum mechanics. Relativity handles gravity and space-time beautifully on cosmic scales. Quantum physics rules the microworld of particles and fields. But at the event horizon, both matter. Quantum fields near the horizon predict Hawking radiation, virtual particle pairs where one falls in and the other escapes, letting black holes evaporate over trillions of years. Yet relativity insists nothing escapes once past the horizon. Reconciling these views sparks paradoxes like the black hole information problem, where quantum theory demands information never be destroyed, but classical horizons seem to swallow it forever. When black holes spin or are charged, things get more odd. Space-time moves around with a moving Kerr black hole. This makes an ergosphere outside the event horizon where nothing can stay still in relation to faraway stars. When particles enter this area, they can split in two, with one dropping in and the other leaving with more energy than the first. This is nature's best slingshot, made possible by the black hole's rotation. For charged Reissner-Nordstrom black holes, there are two horizons, an event horizon on the outside and a Cauchy horizon on the inside. Beyond the inner horizon, predictability breaks down, and physics can't even in theory predict what will happen in the future. Even with all of these problems, the event horizon is still the dividing line. Outside of it, you can get away, but inside, all paths lead inward at or faster than the speed of light. Geography is always there, and no rocket, photon, or smart trick can change that. From the outside, the horizon looks like a sphere of complete darkness. The only shadow that can be seen is the glow of falling matter around it before it goes away. In 2019, the Event Horizon Telescope took a famous picture of this shadow around the giant black hole in galaxy M87. The picture perfectly matched Einstein's equations, proving that the horizon really exists. Singularities at black hole cores. When you're inside a black hole, there's only one point which can't be changed. It looks like the event horizon, but it's not real in the sense of physics. Based on Einstein's ideas, matter is pushed toward the center by gravity once it crosses the horizon. As time goes on, space-time bends more and more, densities rise, and less space is needed. Eventually, everything falls into a single point with no volume and an infinite density. That point, called the singularity, is where general relativity stops making sense. It does a lot more than just guess science stuff. It says that science as we know it will end. Let's start with what Einstein's theory actually says. General relativity describes gravity not as a force, but as the curvature of space-time itself. Mass and energy tell space-time how to curve. Space-time curvature tells matter how to move. For ordinary stars and planets, this works perfectly. For black holes, though, the math marches toward catastrophe. The Schwarzschild solution for a non-rotating, uncharged black hole shows that once matter crosses the event horizon, all paths forward in time point inward. There's no hovering, no orbiting, only falling, with the radius shrinking to zero in a finite amount of time. At the very center of a black hole, physical quantities like density and space-time curvature shoot toward infinity. For example, the Kretschmann scalar, a number that measures curvature, scales as 1 over r to the 6th power in a Schwarzschild black hole. As the radius r approaches zero, that value blows up to infinity. In physics, when you hit infinities like this, it usually signals that the theory has broken down. It's like dividing by zero in math. The equations still spit out results, but those results don't describe anything real. Not only does the singularity have infinite mass, but it also breaks down prediction. Most of the time, you can figure out what will happen in the future if you know the laws of physics and the starting conditions. At the singularity, those calculations stop giving useful answers inside a black hole. Physics can't figure out what causes what. Einstein didn't like this result and hoped that future improvements to his theory would get rid of singularities. But in 1965, mathematician Roger Penrose proved otherwise. His singularity theorems showed that under very general conditions, if matter has positive energy density and gravity always attracts, singularities form inevitably during gravitational collapse. They weren't mathematical artifacts of perfect symmetry. They were baked into the structure of general relativity itself. For this work, Penrose shared the 2020 Nobel Prize in Physics. Black holes that spin and are charged make things even more complicated. In Kerr's answer for spinning black holes, the point singularity is switched out for a ring singularity, which is a loop in one dimension that is hidden inside the inner boundaries. The math says that if someone falls through the ring, they might go through other parts of space-time, or even other worlds, and not hit the singularity at all. Charged Reissner-Nordstrom black holes have similar shapes, with many horizons and paths that look like wormholes. But most scientists think these traits wouldn't last in the real universe. Any disturbance, any stray particle, would probably destroy the delicate inner horizons, squishing everything into a single, crushing point. In either case, relativity can't explain what's going on at the center. We need a quantum theory of gravity, which is a system that brings together general relativity and quantum physics in order to understand singularities physically. Some theories, such as loop quantum gravity and string theory, say that singularities might be replaced by strange structures, such as tiny loops of spacetime, higher dimensional branes, or quantum bounces, in which collapse causes growth into new areas of spacetime. What looks like a point with an infinite density in classical relativity in these pictures is actually a place where quantum geometry takes over, and there are no infinities at all. One clue comes from black hole thermodynamics. In the 1970s, Stephen Hawking showed black holes emit faint thermal radiation due to quantum effects near the horizon. If black holes evaporate completely over trillions of years, what happens to the singularity inside? Does it vanish harmlessly, or does it leave behind a Planck-scale remnant containing all the information about what fell in? The black hole information paradox arises because quantum mechanics insists information can't be destroyed, but classical singularities seem to erase it completely. Resolving this paradox may require understanding singularities at the quantum level, where spacetime itself becomes granular or fluctuating. Cosmic censorship conjecture, proposed by Penrose, tries to keep singularities hidden behind event horizons, ensuring they never affect the external universe directly. A naked singularity, exposed to distant observers without a horizon, would let physics fail in plain sight, destroying predictability outside the black hole as well. Most physicists hope cosmic censorship holds universally, preserving the orderliness of external spacetime. But no theorem yet proves it, and some solutions in general relativity, like the Kerr metric with extreme spin, do allow naked singularities under idealized conditions. Neutron star cores beyond nuclear limits. Black holes crush matter so hard that the laws of physics break. Neutron stars, on the other hand, stop just short of that final fall. These supernova leftovers, which are made up of pieces of stars, pack more mass than the Sun into a sphere that is only 20 kilometers wide. Gravity so strong that it bends light into rings, and magnetic fields a trillion times stronger than Earth's make their surfaces even harder to understand. But the really strange stuff is deep below the rock, where the densities are higher than anything that atomic nuclei can handle on Earth. In the cores of neutron stars, science is very close to not knowing what will happen. Ordinary atoms consist of nuclei surrounded by electron clouds. Crank up the pressure, far beyond anything in planets or white dwarfs, and electrons get squeezed into the nuclei themselves, merging with protons to form neutrons. That's why neutron stars are named as they are, whole sun masses of material crushed into a single giant nucleus, made almost entirely of neutrons packed shoulder to shoulder. But this picture only holds for a while. Once density rises above nuclear levels, about 2.8 times 10 to the 14th grams per cubic centimeter, even neutrons, once thought unbreakable in astrophysical settings, may collapse into more exotic states of matter. The cores of neutron stars cross this threshold, entering conditions that our current theories struggle to describe. Neither experiments on Earth nor simple calculations can fully capture how matter behaves under such extreme pressures and densities. Hyperons are particles that have strange quarks along with the normal up and down quarks that are found in protons and neutrons. At high numbers, it might be energetically beneficial to make hyperons instead of normal nuclear matter, which would create a soup full of hyperons. But this brings up the hyperon puzzle. Hyperons change the equation of state, which is how pressure and density are related. This means that neutron stars fall into black holes at lower masses than scientists think they have. To keep stars steady, the equation of state must get stiffer at even higher densities. This could be because of hyperon interactions that push things away or quark matter phases. Prion or kaon condensates are mentioned in another idea. In these situations, mesons, which are particles that control nuclear forces, fill the center like a superfluid with group quantum states. Instead of individual particles moving around, the core acts like a single large quantum object, which changes the rate of cooling, spinning, and pressure in ways that are still not fully understood. At densities several times nuclear saturation, quarks themselves, the fundamental building blocks inside protons and neutrons, might roam freely in a quark-gluon plasma, no longer confined inside individual particles. This would turn the inner core into something resembling conditions microseconds after the Big Bang. Deconfined quark matter at billions of degrees and crushing pressures, a tiny relic of the universe's earliest moments surviving inside every neutron star. Some ideas say that this area could have color superconductivity, where quarks pair up like electrons do in normal superconductors. This would allow nuclear matter to carry color charge with no resistance. At the highest densities, phases like the color flavor locked state, which includes all three types of quarks, up, down, and weird, could become dominant. This would make matter that is completely different from anything that has been seen in a lab. The hard part is making sure of any of this. Neutron star cores are buried under kilometers of solid rock, so we can't drill down or take samples directly. Astronomers figure out what's going on inside neutron stars by looking at their masses, sizes, spins, cooling rates, and gravitational waves. For example, the finding of neutron stars with masses higher than 2 solar masses rules out equations of state that are too soft and break too easily. X-ray studies of hotspots on spinning neutron stars limit radii and test how stiff or soft matter gets at nuclear densities. Gravitational wave astronomy recently joined the game. The 2017 neutron star merger GW170817 produced ripples in spacetime, carrying information about how neutron stars deform tidally before colliding. Stiffer equations of state make stars resist squeezing, altering the gravitational wave signal compared to softer equations predicting more compact stars. As detectors like LIGO, Virgo, and CAGRA improve, future mergers will pin down neutron star interiors with unprecedented precision. Cooling behavior offers more clues. Young neutron stars radiate X-rays as they shed residual heat from formation, but the rate depends sensitively on interior composition. Exotic phases like pion condensates or quark matter open rapid neutrino cooling channels, making stars dim faster than ordinary nuclear matter would allow. Observing thermal evolution over decades tests whether such processes operate deep inside. Magnetic and rotational phenomena complicate things further. Pulsars, rotating neutron stars beaming radio waves, sometimes glitch, spinning up abruptly as if internal superfluids transfer angular momentum to the crust. Modeling these glitches requires understanding how nuclear matter at different depths couples or decouples under extreme densities and magnetic fields. Even after decades of research, there is still no agreement on what really fills neutron star cores. Are they full of hyperons? Quark matter mix-ups? Do completely new states of matter appear that QCD can't explain? Physicists are puzzled by all of these possibilities because particle colliders like the LHC and RHIC have very high temperatures but not very high densities. This is different from neutron stars, which are very cold and very dense. Astrophysics, then, studies levels that can't be reached on Earth. It turns the night sky into a laboratory for studying nuclear and particle physics at their most extreme. Magnetar surfaces and quantum critical fields. If neutron star cores push matter to its densest limits, magnetars do something different to make the physical world go crazy. They turn up magnetic fields so high that quantum electrodynamics, the theory that explains how light and matter interact, starts to break. A normal neutron star carries a magnetic field of about 10 to the 12th Gauss. For scale, Earth's magnetic field is only about half a Gauss, and the most powerful steady magnets built in laboratories reach around 10 to the 5th Gauss. Magnetars blow past all of that. Their surface fields reach 10 to the 15th Gauss, 1,000 times stronger than ordinary neutron stars and trillions of times stronger than Earth's field. Deeper inside, they may climb to 10 to the 16th or even 10 to the 17th Gauss. These aren't just record-breaking numbers. They exceed a key physics limit known as the quantum critical field, about 4.4 times 10 to the 13th Gauss, where quantum effects completely change how matter and light behave. Above this limit, magnetic forces on charged particles rival their rest energy, reshaping the vacuum itself. Electrons spiral so tightly around field lines that their motion perpendicular to the field becomes quantized into discrete energy levels called Landau levels. Ordinary atomic structures collapse. Atoms stretch into narrow cylinders aligned with the field, turning three-dimensional matter into one-dimensional strings of nuclear charge wrapped in electron clouds. Chemistry as we know it stops working. But the influence of a magnetar's field doesn't end with atoms. At strengths of around 10 to the 15th Gauss, even empty space becomes strange. Quantum electrodynamics predicts that the vacuum teems with virtual electron-positron pairs flickering in and out of existence. In fields this strong, those pairs line up, polarizing the vacuum so that empty space acts like a birefringent crystal. Light waves of different polarizations move at slightly different speeds. This effect, called vacuum birefringence, has been hinted at in X-ray polarization studies of neutron stars, such as RxJ 1856, 3754. A direct detection would confirm quantum effects on spacetime itself under conditions we could never reproduce in the lab. These magnetic fields also drive the violent behavior of magnetars. As the crust shifts and cracks under immense magnetic stress, field lines twist, reconnect, and snap explosively, releasing colossal amounts of energy as bursts and flares. The December 27, 2004 giant flare from SGR 180620 is the prime example. It blasted out about 10 to the 46th ERGs in less than a second, more energy than the Sun radiates in 100,000 years, and for a brief moment, it outshone the entire Milky Way in gamma rays. Such events likely come from magnetospheres, where fields exceed the quantum critical threshold, accelerating particles to extreme energies and spawning cascades of electron-positron pairs. In such fields, even basic physical processes warp. Photons, normally massless particles moving at light speed, can split into pairs of lower energy photons, a process forbidden in ordinary conditions, but allowed when magnetic fields polarize the vacuum strongly enough. Conversely, gamma rays can convert directly into electron-positron pairs without colliding with matter, provided the magnetic field supplies the necessary momentum conservation. These exotic QED processes remain poorly tested because no earthly experiment reaches 1013, 1015 Gauss, leaving magnetars as our only laboratories. More scope is added by surface layers. Near the crust, magnetic pressure is so strong that it overpowers gravity. This causes heat to flow, breaks the crust into starquakes, and confines plasma into coronae that are controlled by magnetic fields. Some models compare Magnetar magnetospheres to solar flares on steroids. Twisted magnetic loops expand above the surface, then explode back together and rain energetic particles back onto the crust. Telescopes like Fermi and Swift can see these hard X-rays and soft gamma rays. Above the surface, magnetic fields trap electron-positron plasmas into magnetospheres where radiation pressure, particle acceleration, and quantum effects intertwine. Some theories suggest magnetospheres become so dense with pairs after giant flares that they form fireballs confined by closed magnetic loops, radiating X-rays for minutes before collapsing back onto the star. Even gravity itself isn't immune to magnetar fields. If the internal field climbs above about 10 to the 17th Gauss, it can actually distort the star's shape, stretching it into a football-like form or flattening it like a pancake, depending on the field geometry. As the star spins, these distortions would make it emit continuous gravitational waves, offering detectors like LIGO a way to sense magnetic stresses deep inside indirectly. Astronomers recognize magnetars through three main signals. First, steady X-ray emission caused by magnetic field decay heating the crust. Second, frequent short bursts lasting only fractions of a second, each releasing between 10 to the 38th and 10 to the 41st ergs. And third, the rare but spectacular giant flares, which release 10 to the 44th to 10 to the 46th ergs in an instant, powerful enough to be detected across entire galaxies. White hole hypotheticals in relativity. Astrophysics news is mostly about black holes, but Einstein's equations also include a much stranger possibility, the white hole. A black hole is nature's ultimate trap because it's where matter and light disappear forever. A white hole, on the other hand, is the exact opposite. Nothing can ever fall into it, only go out. Time seems to be going backwards. Matter, energy, and even light would shoot outward, never going inside or crossing the barrier to the inside. That idea is so far-fetched that many scientists don't believe white holes exist at all. But when Einstein's equations for spacetime are solved under certain conditions, white holes appear naturally. The story starts with the Schwarzschild solution, the simplest description of a non-rotating, uncharged black hole. Solve the equations fully, including regions outside our observable universe, and you get not only a black hole with an event horizon and singularity, but also a mirrored region on the other side, a white hole, spewing matter outward, where time runs in reverse compared to the black hole interior. The two connect via a mathematical bridge called an Einstein-Rosen bridge, or wormhole, linking black and white hole regions through spacetime itself. Black holes and white holes are two sides of the same spacetime structure in this made-up picture. The black hole eats matter, and the white hole throws it somewhere else, or else when. The wormhole throat, which is the bridge between them, pinches off too quickly for anything to actually cross it, but the formulae say that both sides exist theoretically. But problems show up right away in the body. We can't understand how white holes work because they need carefully planned starting conditions, a universe where a singularity already exists and has been spilling matter outward forever without ever collapsing. Black holes form naturally when huge stars fall apart under the force of gravity. White holes, on the other hand, would have to exist from the beginning, which doesn't seem likely unless new physics makes them appear on their own. They also appear violently unstable. Any matter or radiation approaching a white hole horizon, no matter how small, triggers gravitational back reaction that collapses the white hole into an ordinary black hole almost instantly. Even the tiniest disturbance destroys the time reverse solution. That's why most physicists consider white holes mathematical artifacts rather than real astrophysical objects. Yet the idea keeps resurfacing, especially in quantum gravity contexts. Some researchers speculate that black hole singularities might bounce due to quantum effects, with collapsing matter reaching Planck densities before rebounding outward. Instead of ending in a singularity, the interior forms a white hole, ejecting material back into the universe after some delay. From outside, this might look like a long-lived black hole evaporating via Hawking radiation, but deep inside, a quantum bridge connects collapse and explosion across vast timescales. This black-to-white hole transition appears in approaches like loop quantum gravity, where spacetime has discrete quantum geometry at the smallest scales. There, gravity becomes repulsive at ultra-high densities, preventing true singularities and replacing them with bounces. A black hole might then become a white hole after millions or billions of years, releasing information thought lost beyond the event horizon, and perhaps resolving the black hole information paradox. In a different way, white holes are linked to Planck scale matter. If Hawking radiation makes black holes disappear until they reach quantum gravity levels, then the last step might be a stable or metastable white hole residue, which is a tiny object that slowly leaks information instead of going away completely. Such leftovers could hold the data of everything that has ever been eaten, meeting the requirements of unitarity in quantum physics while avoiding singularities. In some models of the universe, white holes can even be seen. Some experts think that the Big Bang might be like a white hole, an event where matter, energy, and spacetime shoot outward from a dense starting point that never had a collapse phase in our own universe. This doesn't mean that our universe came from the other side of a black hole in a parent universe, but the mathematical similarity is interesting to people who study circular or bouncing cosmologies. There are no known white holes. Some fast radio bursts, FRBs, which are millisecond flashes of radio waves from galaxies far away, have been suggested as signs of possible white hole explosions. However, magnetars and other cosmic engines are much more likely causes. Also, gamma-ray bursts were once thought to be possible, but again, they can be explained by massive stars falling or neutron stars merging, which don't involve strange things in spacetime. Even so, white holes won't go away in theoretical physics because they show us where general relativity stops being useful. If singularities really do mean the end of physics, then fixing them will probably require new rules. White holes are one possible result once quantum gravity takes over. Do they exist as real things in space, as rare quantum events, or as illusions in our equations? No one knows yet. Cosmic strings and early universe defects. The universe was a boiling pot of energy and particles long before there were stars, planets, or galaxies. It was hotter and denser than anything we can make on Earth. There was a time, not long after the Big Bang, when physics as we know it began to form from something more basic. There may have been a time when all the forces that we know of today, like gravity, electricity, and the strong and weak nuclear forces, were one and could be explained by a single structure. In a series of phase changes, like water turning into ice, these forces froze out or split apart as the universe grew and shrank. And just like how freezing water catches air bubbles or cracks as it hardens, spacetime may have grown flaws or topological defects during these early changes. Cosmic strings are one of the most interesting of these. These are made up very thin lines of energy that stretch across the universe and break or bend the usual rules of physics. Cosmic strings are not strings like in string theory. They're closer to cracks in spacetime itself. Imagine the early universe filled with fields, like the Higgs field responsible for giving particles mass. As the universe cooled, these fields settled into stable configurations, but sometimes different regions made incompatible choices about the field's lowest energy state. Where such regions met, defects formed, boundaries where the field couldn't fully settle, locking in enormous energy densities. In 3 dimensions, these defects could be point-like, monopoles, surface-like, domain walls, or line-like, cosmic strings. A single cosmic string might be thinner than a proton, yet weigh as much as a mountain per meter, because all its mass energy is concentrated into a nearly one-dimensional line. Cosmic strings change the shape of spacetime around them in strange ways. They don't have normal gravity pull like black holes do. Instead, they make a cone shape. Should you walk all the way around a cosmic string, you'll find that the angle is less than 360 degrees. This is because the string takes away a piece of spacetime. As light passes on either side, it moves in straight lines but comes out bent. This is called gravitational lensing, and it creates unique effects like double pictures of faraway galaxies without the magnification that normal lenses do. Because cosmic strings carry enormous energy, loops of them oscillating in space would radiate gravitational waves, ripples in spacetime traveling at light speed. Networks of strings crisscrossing the cosmos could produce a stochastic gravitational wave background, a faint gravitational hum from countless vibrating loops over cosmic history. Pulsar timing arrays, which use millisecond pulsars as ultra-precise cosmic clocks, already search for such signals. Intriguingly, recent hints of a nanohertz gravitational wave background reported by collaborations like Nanograv sparked speculation about cosmic string networks, though merging supermassive black holes currently provide a simpler explanation. Strings might also see density fluctuations in the early universe, acting as gravitational wells around which matter gathered to form galaxies. In the 1980s, cosmic strings were leading candidates for explaining large-scale cosmic structure before precision measurements of the cosmic microwave background, CMB, shifted attention toward quantum fluctuations during inflation instead. Still, cosmic strings could leave faint imprints on the CMB as line-like discontinuities or temperature steps, signatures future experiments might yet uncover. Cusps and kinks on rotating string loops are a very strange choice. As loops move, points moving almost at the speed of light could send out long, powerful bursts of gravitational radiation or even high-energy particles if the strings combine with other fields. It would be proof of cosmic strings and help us understand physics at energy levels billions of times higher than any human-made collider if we could find these bursts. Cosmic strings also show up naturally in some grand unified theories, models that merge the strong, weak, and electromagnetic forces at energies above 10 to the 16th giga-electron volts, close to the conditions of the Big Bang. If these theories are right, cosmic strings would be fossil relics from that era, leftovers of physics far beyond the standard model. Once formed, they could survive for billions of years, since only quantum gravity itself would have the power to destroy them. Still, there is no proof of cosmic strings yet. After looking at the sky for decades, no gravitational lensing patterns or CMB fingerprints were found that matched string theories. The LIGO and Virgo gravitational wave detectors don't see any bursts from string cusps that are stronger than what they can detect now. All of these results don't completely rule out strings, though. They only limit how thick or active a network can be right now. The Planck length and Planck timescales. The Planck scale takes us to the smallest lengths and shortest times, where the very idea of spacetime may break apart. Cosmic strings take us to the biggest scales that were shaped by the physics of the early universe. In this case, quantum mechanics and general relativity hit each other so hard that neither theory can stand on its own. Instead, scientists expect a whole new structure called quantum gravity to form. The Planck length and the Planck time are the two numbers that show this edge. These aren't just made-up ideas. They are found by adding together three basic constants: the speed of light, c/c/c, Newton's gravity constant, g/g/g, and Planck's constant, h/h. From them, you can make numbers that have length and time dimensions that are probably too big for our present physics to handle. The Planck length, written as L sub p, is defined as the square root of h bar times g divided by c cubed. Narrated fully, L sub p equals the square root of h bar multiplied by g divided by c cubed. Numerically, it comes out to about 1.6 times 10 to the minus 35th meters. That's about 20 orders of magnitude smaller than a proton. It's not just small, it's so tiny that even the most powerful particle accelerators today can't come close to probing it directly. The Planck time, written as t sub p, is the Planck length divided by the speed of light. Narrated tt sub p equals the square root of h bar multiplied by g divided by c to the fifth power. Numerically, it is about 5.4 times 10 to the minus 44 seconds. That is the time it takes light itself to travel one Planck length. Why do we care about these numbers? Because they show the sizes at which quantum uncertainty and gravity are both very strong. As things get bigger, quantum physics rules the world of particles, while gravity forms planets, stars, and galaxies. You don't have to think about gravity or quantum effects when you're studying atoms or figuring out the paths of planets. But as distances get closer to the Planck length, gravity becomes stronger because space-time curves more when energy is crammed into a small area. Around 10 plus dege meters, there is so much energy in the space-time itself that quantum changes can't be ignored. Einstein talked about a smooth cloth that changes into something rough, maybe discrete or foamy. In this case, the classical idea of a well-defined shape is no longer valid. Physicists call this hypothetical regime quantum foam or spacetime foam. At the Planck scale, uncertainty might blur distances and times so completely that talking about before and after, here and there, loses meaning. Spacetime might flicker between topologies, create microscopic black holes, or consist of fundamental building blocks like strings or loops rather than points and curves. Heisenberg's uncertainty principle says that to confine a particle to a smaller area, it needs more momentum, which means it needs more energy. At the Planck length, the energy needed to look at such small areas would gather enough mass and energy in one place to create a black hole the size of a house. This would hide the area you were trying to see behind its own event horizon. Not only does measurement not work below this point, it also breaks down literally. Theorists propose various ideas for what replaces classical spacetime here. String theory suggests one-dimensional strings vibrating at Planck lengths replace point particles, smoothing out singularities. Loop quantum gravity envisions spacetime itself made of discrete loops or spin networks with finite volumes and areas, eliminating infinities by giving geometry a quantum structure. Other approaches invoke causal sets, holographic principles, or emergent spacetime from deeper quantum information laws. Experimentally, the Planck scale is far out of reach. Particle accelerators like the Large Hadron Collider explore energies of about 10 to the 13th electron volts, while Planck energies would require around 10 to the 19th giga electron volts, 1 trillion times higher. Building a collider that powerful would need a ring larger than the entire Milky Way galaxy. But cosmic environments might give us hints that aren't so clear. If space-time has a separate structure at the Planck scale, there could be small breaks in Lorentz invariance, which says that space and time should be symmetrical. That might change how photons with a lot of energy move over billions of light years. If our instruments get accurate enough, we might be able to see these small differences when we look at gamma-ray bursts, blazars, or even gravitational wave signs. In math, the Planck length also sets the size range where the entropy and temperature of a black hole meet quantum rules. If you divide the horizon area by 4 times the Planck length squared, you get the Bekenstein-Hawking entropy of a black hole. In full, S is equal to the area divided by 4 times L squared. This relationship suggests that space-time stores information not by volume, but by surface area. That idea inspired what is called the holographic principle, the possibility that all the physics inside a region could be fully described by information written on its boundary. Many physicists see this as one of the strongest clues to the true nature of quantum gravity. Big Bang singularity physics limits. Planck time and Planck length are the smallest relevant scales in physics. The Big Bang singularity is where all of those limits meet. If you go back in time through cosmic history, you can see galaxies rushing toward each other and stars and nebulae getting closer together. Eventually, all matter, radiation, and even space-time itself seem to converge on a point about 13.8 billion years ago, when the temperature and density were infinite. At time zero, this singularity isn't just a place with very bad conditions. It's also the point at which general relativity, which is our best theory of gravity, stops working at all. To see why, start with Einstein's equations. General relativity treats the universe as a smooth fabric of space-time curved by mass and energy. In 1922, Russian physicist Alexander Friedmann solved these equations for a homogeneous isotropic universe and found something radical. If cosmic expansion runs forward now, it must have been denser and hotter in the past. Mathematically, rewinding far enough makes density and curvature blow up to infinity in finite time. The Friedmann-Lemaitre-Robertson-Walker FLRW metric describing cosmic expansion leads straight to a singularity unless something intervenes. By the middle of the 1900s, evidence started backing up the Big Bang idea. Edwin Hubble discovered that galaxies are moving away from each other, showing that the universe is expanding. Then, in 1965, scientists found the cosmic microwave background, faint leftover radiation from when the universe was only 380,000 years old and about 1,000 times smaller than today. If you trace this expansion backward, the universe gets hotter and denser. First, atoms break apart, then even nuclei fall apart, and finally protons and neutrons themselves melt into smaller particles called quarks and gluons. Go back further. At about 10 to the minus 12 seconds after the start, the electroweak forces combine into one. At about 10 to the minus 36 seconds, a rapid growth phase called inflation may have happened. But before 10 to the minus 43 seconds, known as the Planck time, our equations stop working. At that instant, density shoots past 10 to the 93rd grams per cubic centimeter, and temperature climbs above 10 to the 32nd kelvins. In such extreme conditions, the normal rules of physics break. General relativity predicts infinite curvature, while quantum theory assumes space-time is smooth. The two disagree, and no theory we have today can handle it. The singularity, the supposed point of the Big Bang, isn't really a place where things end, but more like a warning sign that says, our current theories can't go further back. In classical physics, you need a before to set the starting conditions, but at the Big Bang, time itself starts there, so there is no before. Inflation, the idea that a small area of space grew at an amazing rate in the first 10 to the minus 36 seconds, gives us a hint. On a big scale, the universe looks smooth, but there are actually tiny waves that grow into galaxies and clusters. These are caused by inflation. But inflation doesn't get rid of the singularity, it just moves it ahead a little. Why did everything begin? That is still a big question that needs to be answered by new physics. This is the reason scientists look for options for quantum gravity. A branch of loop quantum gravity called loop quantum cosmology replaces the Big Bang with a big bounce. In this theory, the universe first contracts until it hits a minimum volume at Planck densities, and then it expands again. Here, quantum geometry gives spacetime a distinct structure by applying the smallest length scale possible. This stops spacetime from curving infinity times infinity. String theory adds a new variation. Fundamental strings, also called branes, are used instead of point particles in string theory. They smooth out singularities by adding extra dimensions or extended geometry. In some models, like the ekpyrotic model, the Big Bang is seen as a clash between branes of higher dimensions, with time going back infinitely before the beginning of the universe. Stephen Hawking and James Hartle's no-boundary ideas are even stranger. They say that spacetime close to the Big Bang acts like a four-dimensional sphere. It has limits but no edges. So the idea of before the Big Bang is like the idea of north of the North Pole. Probing such early times remains daunting. The cosmic microwave background lets us see back to 380,000 years after the Big Bang. But earlier epochs stay hidden because the universe was opaque to radiation. Primordial gravitational waves, ripples in spacetime from the universe's first moments, could carry information directly from the Planck era if inflation amplified them enough, leaving faint polarization patterns in the CMB, or detectable signals for future observatories like LISA or CMB-S4. Black hole firewall paradox regions. With event boundaries, singularities, and spacetime that is so skewed that not even light can get out, black holes already change the way things are. However, theoretical scientists found a puzzle in 2012 that made us question everything we thought we knew about them. The black hole firewall paradox is a strange conflict between Einstein's theory of relativity and quantum physics. It promises a wall of burning energy at the event horizon that is strong enough to destroy anything falling in. Quantum physics, on the other hand, changes things. Stephen Hawking found out in 1974 that black holes aren't completely black. Hawking radiation is made by quantum fields close to the horizon. It is made up of pairs of virtual particles, one of which goes to infinity and the other falling in. Over unimaginable amounts of time, this radiation causes black holes to slowly disappear, getting smaller and smaller until there is nothing left. The issue is that unitarity is required by quantum theory, which means that data about a system's actual state can never be lost. But Hawking radiation looks like temperature radiation, which is featureless and doesn't tell you anything about what fell in. Where does that information go when the black hole goes away for good? Quantum physics doesn't work if it's gone for good. We need a way for it to get away that works with both quantum theory and general relativity. For decades, physicists suspected subtle quantum correlations, entanglement, might carry the information out. Hawking radiation particles outside the horizon would stay entangled with interior states, preserving information until some unknown quantum gravity effect releases it near the end of evaporation. This picture keeps the horizon smooth, honoring Einstein's equivalence principle, while quantum mechanics handles the bookkeeping. Then came 2012. Physicists Almheri, Marolf, Polkinski, and Sully, AMPS, examined what happens late in a black hole's life, after it has radiated half its mass, the so-called page time. By then, early Hawking radiation far away must remain entangled with later radiation to preserve information. But quantum mechanics forbids a single system from being maximally entangled with two independent partners. If outgoing radiation stays entangled with earlier radiation to save unitarity, it can't also stay entangled with interior particles to keep the horizon smooth. Something has to give. The AMPS team argued the interior must be sacrificed. Instead of a serene crossing, the horizon becomes a high-energy firewall, wherein falling observers burn instantly as entanglement links snap violently. This preserves unitarity. information escapes in the radiation, but destroys Einstein's equivalence principle by turning the horizon into the hottest, deadliest surface in the universe. The science world backed away. As long as relativity's smooth spacetime was followed, black holes had always had no drama at the horizon, which meant that there was nothing unusual in that area. Firewalls took away that beauty and put something harsh and ugly in its place, a single point not in the middle but right on the edge. Resolutions were put forward quickly. Some people think that quantum gravity effects like ER equals sine EPR, which is the idea that particles that are linked can join through tiny wormholes, could make the inside and outside worlds work together without any walls. Others used complementarity, which means that no single viewer sees violations. Observers who are close to the action see smooth horizons, while observers who are far away say that information is escaping. There is no conflict because no one sees both points of view. Calculations using the ADS-CFT correspondence, a holographic idea that links gravity in higher dimensions with quantum field theories in lower dimensions, suggest that black holes do preserve information. In this picture, the lost data hides in subtle correlations within Hawking radiation. Some models even recreate the so-called page curve, a graph that shows information leaking out in a way consistent with quantum mechanics, without needing anything as wild as a firewall. But scientists don't fully agree yet. The firewall paradox is still unsolved because it forces three major principles of physics to clash with each other. First, unitarity, the rule in quantum mechanics that says information can never be destroyed. Second, the equivalence principle, the rule from relativity that says free fall should feel smooth and crossing a horizon shouldn't be special. Third, quantum field theory in curved spacetime, the rule that Hawking radiation comes from normal quantum fields near a black hole's horizon. The paradox is that all three can't hold true at once, and we don't know which one, if any, has to give way. Wormhole throat geometries. Wormholes are like tubes that link different parts of space and time through a shortcut that is hidden in higher dimensions. Black holes bend space-time into one-way traps. Einstein and Rosen came up with the idea in 1935. They found a way to solve the general relativity problem that is now known as the Einstein-Rosen bridge. This bridge is a mathematical link between two black holes that makes a throat through space-time. At first glance, these bridges look like they would be fun to ride on in science fiction. Going in one mouth and out the other is light years away, so you don't have to go through normal space. Einstein-Rosen bridges fall apart too fast for anything to cross though, which is hidden by mathematics. At light speed, their necks pinch off, cutting the link before signals or matter can cross it. In math, they're like mirages. They show up in equations, but don't show up in real life. The real breakthrough came in 1988, when physicists Morris and Thorne analyzed what it would take to keep a wormhole throat traversable, open long enough for particles, people or photons to pass through safely. The catch? Traversable wormholes require matter with negative energy density, something violating the standard energy conditions of relativity. In ordinary physics, energy densities stay positive. Gravity attracts. Negative energy, however, would make gravity repulsive, counteracting the throat's tendency to collapse. Is there bad energy? Yes, which is surprising, at least in quantum physics. There are places in a vacuum where the quantum field energy drops below zero because some wavelengths can't fit between the two plates. This is called the Casimir effect. It's a very small effect, much too small to hold open a cosmic tunnel, but it shows that negative energy levels are possible in nature, even though it seems impossible to build them on a large scale right now. A wormhole throat that can be traversed has two important radii, the mouth radius, which shows where passengers enter or leave, and the throat radius, which is the narrowest cross-section between the two areas. For the throat to stay open, it needs unusual matter to put out enough negative pressure to keep the curve of space-time in check. If it's not there, gravity will close the throat before anything can get through. Wormholes are odd, even if strange stuff does exist. In some arrangements, closed time-like curves are possible. These are loops in spacetime that let people go back to their own pasts, which can cause problems with causality, like the grandfather paradox. Physicists argue about whether quantum effects like Hawking's chronology protection theory would make these time machines unstable and destroy them with an endless amount of energy before paradoxes happen. Others explore whether wormholes connect not just two places in our universe, but two entirely separate universes. In the maximally extended Schwarzschild solution, each mouth lies in a different asymptotically flat spacetime, so nothing entering one mouth emerges in the same universe at all. Collapsing stellar black holes wouldn't form such connections naturally. They likely pinch off into singularities instead. But in anti-de Sitter ADS spacetimes with negative cosmological constant, certain wormholes might stay open through quantum effects. The ER equal sign. EPR conjecture proposed by Maldacena and Susskind in 2013 links wormholes, Einstein-Rosen bridges, to quantum entanglement, Einstein-Podolsky-Rosen pairs. In this view, entangled particles connect through non-traversable wormholes in higher dimensions. While you can't send signals through them, the geometry offers a striking picture. Space-time connectivity itself may arise from patterns of quantum entanglement. Traversable wormholes appear again in modified theories of gravity and semi-classical setups, using quantum fields violating classical energy conditions. In 2017, physicists Gao, Jafferis and Wall showed that quantum effects could make certain ADS wormholes traversable by injecting negative energy shockwaves, letting information pass through without breaking causality or relativity. Could nature build such objects? If microscopic wormholes formed in the early universe, they might survive today as primordial relics, though no evidence exists yet. Some dark matter models even speculate that hidden wormholes could mimic black holes gravitationally, while lacking horizons or singularities, distinguishable only through subtle gravitational wave signals during mergers. In math, wormhole mouths follow the flaring out condition, which says that the shape of space-time near the throat must curve outward instead of inward. This means that negative energy levels are needed, which goes against the null energy condition of general relativity. This can't be met by classical matter. Wormholes could only use quantum fields or made up strange fluids like phantom energy, naked singularity formation zones. This is how black holes keep what happens in their event horizons from affecting the rest of the universe. They hide their singularities behind them. Roger Penrose first suggested this idea of cosmic control in 1969. It makes space-time predictable because no one outside the horizon ever sees physics fail at the singularity itself. But what if gravity stops being humble every once in a while? What if collapse creates a naked singularity that is open to the whole universe and doesn't have an event horizon to hide it? There are exact answers to Einstein's equations that do have open singularities. The most well-known example comes from the Kerr measure, which describes black holes that spin around. When the dimensionless spin parameter am is less than 1, or when spin is below a critical limit, the singularity stays hidden behind the inner and outer boundaries. If you raise the spin above this limit, so that am is greater than 1, the boundaries disappear, leaving only the singularity. This created a ring singularity that is infinitely thick and sits open in the middle. Around it are areas where space and time behave in unpredictable ways. Physicists debate whether such overspinning objects could form in reality. In theory, you might try to overspin a Kerr black hole by bombarding it with particles carrying angular momentum. But calculations suggest subtle effects, like radiation reaction and self-force corrections, prevent horizons from disappearing. Nature seems to enforce cosmic censorship dynamically, though no general proof exists for all scenarios. A similar pattern can be seen in the Reisner-Nordstrom measure for charged black holes. Boundaries are lost when there is too much electric charge compared to mass, leaving a single point. Again, realistic collapse probably quickly gets rid of any extra charge by making pairs or letting plasma fall in before the boundaries disappear. It looks like the universe doesn't want to show us its singularities, but math leaves the door open. There are also models of gravity collapse, such as the Tolman-Bondi answer for dust clouds. When certain conditions are present at the start, like uneven density profiles, the falling cloud forms a singularity that can be seen from far away before it is trapped by the horizon. In models of spherical collapse that are tuned just right, these locally naked singularities show up. However, small changes often bring back the boundaries, which suggests that these cases might be non-generic fine-tuning artifacts rather than real astrophysical results. If naked singularities did exist, what would they look like observationally? Without horizons, infalling matter and radiation could interact directly with regions of extreme curvature, perhaps producing high-energy emissions or gravitational wave signals unlike anything black holes generate. Some researchers speculate that mysterious cosmic phenomena, ultra-high-energy cosmic rays, or peculiar gamma-ray bursts, might arise from physics near naked singularities, though no evidence yet supports this. Theoretically, naked singularities break predictability because general relativity becomes incomplete when curvature blows up in regions visible to the outside universe. Normally, Einstein's equations let you evolve initial data forward in time uniquely, but near a naked singularity, multiple extensions of spacetime become possible beyond the singular point, with no rule choosing among them. Physics loses its script. Anything might emerge, unconstrained by prior conditions. Some ideas in quantum gravity suggest that singularities might not stay true singularities once quantum effects take over. Instead of infinite curvature, Planck-scale physics could replace them with strange but finite states of matter or spacetime. Possibilities include quantum bounces, fuzzballs, or gravastar interiors. If that's the case, what we call a naked singularity might actually be a window into brand new physics rather than a dead end. Finding one could let us study quantum gravity directly instead of relying only on indirect hints from cosmology. The idea of cosmic censorship tries to keep singularities under control, and it comes in two versions. Weak cosmic censorship says singularities are always hidden behind event horizons, so distant observers never see them directly, and the universe stays predictable from the outside. Strong cosmic censorship goes further, saying that no observer anywhere, even locally, should face a breakdown of predictability. In this view, spacetime must remain globally well-behaved and deterministic, with no cracks showing through. Closed time-like curve regions in Kerr spacetimes. In general relativity, the Kerr metric for spinning black holes is one of the weirdest ways to describe black holes. Kerr black holes twist spacetime as they spin, unlike the simple Schwarzschild black holes that look like spheres. It's like watching water swirl down a drain. Equations that describe space and time act in such a strange way inside their limits that they allow for shocking things to happen, closed time-like curves, or CTCs. These are paths through spacetime that loop back on themselves, letting a person go back to their own past. First, let us talk about what time-like means. A time-like path in relativity is a path that any mass-containing object can follow. It stays inside the light cone at all times, moving slower than light, but always forward in time locally. Usually, tracks through time don't cross. You can't leave your house on Tuesday and come back on Monday along the same world line. Causality, the idea that reasons come before outcomes, stays the same. But in Kerr spacetimes, the rotation twists spacetime so strongly inside certain regions that the light cones themselves tip over. At some radii inside the inner horizon, the Cauchy horizon, the tipping becomes so extreme that the time direction closes back on itself. A future-directed time-like curve can loop through spacetime and return to the same event where it started, forming a closed time-like curve. This is because of the strange shape inside the Kerr black hole, which is a mathematical fact. The ergosphere is outside the event horizon. Every object in this area is dragged around in spacetime, which makes them spin at the same speed as the black hole. If you cross the outer horizon, motion toward the center will always happen. If you cross the inner Cauchy horizon, determinism starts to break down. The Kerr solution shows a fantastical scenery beyond it, with wormhole-like portals to other worlds, negative radius regions, and places where CTCs fill spacetime. In terms of physics, this creates clear contradictions. If people, or messages, could follow these curves, they could send information back to the past. This could solve well-known time travel problems like the Grandpa paradox. More generally, physics can't tell you what will happen in the future because knowing the starting conditions doesn't fix how things will change in the future. Do such curves really exist inside astrophysical black holes? Most physicists suspect not. The Cauchy horizon separating normal interior regions from the CTC zone suffers from instabilities. Infalling radiation gets infinitely blue-shifted there, amplifying into destructive energy bursts in what's called mass inflation. These instabilities likely destroy the inner structure entirely, replacing it with a singularity rather than leaving smooth regions containing time loops. Real black holes forming from stellar collapse probably lack the delicate perfection of the Kerr solution needed for CTCs to survive. Still, experts are interested in the math because it shows that general relativity is the only theory that lets causality break down in some situations. Kerr black holes aren't the only ones like this. Kurt Gödel came up with another perfect answer in 1949 called Gödel's universe. It is a rotating universe full of closed time-like curves that doesn't look anything like our expanding universe. Tipler cylinders, infinitely long spinning cylinders, and some traversable wormholes are some other strange spacetimes that can also have CTCs if energy conditions break down or spacetime warps strongly enough. Quantum physics might rescue causality through mechanisms like Hawking's chronology protection conjecture, which speculates that vacuum fluctuations near forming CTCs grow so intense that they destroy the time loop regions before paradoxes occur. Essentially, quantum effects could act like cosmic bouncers, kicking out any would-be time travelers by destabilizing spacetimes that permit them. Even if CTCs inside ideal Kerr black holes never survive in reality, studying them forces physicists to confront deep tensions between relativity and quantum mechanics. Quantum field theory in curved spacetime already struggles near Cauchy horizons because infinite blue shifts make particle energies diverge. A full theory of quantum gravity may smooth out these infinities, replacing classical time loops with something consistent, yet radically different from ordinary causality. Gravastar and dark star interiors. Crossing the event horizon means you will fall into a singularity where physics ends. But what if nature doesn't have any singularities at all? What if the insides of things we call black holes aren't infinite density points, but strange stars made of ultra-dense matter or quantum spacetime itself? This is what inspires models like gravastars, gravitational vacuum stars, and dark stars, which are hypothetical alternatives to black holes that replace singularities with something stranger, but still not singular. The gravastar concept appeared in 2001 when physicists Paul Mazur and Emil Motola proposed a radical picture. Instead of matter collapsing to a singularity, they suggested the interior undergoes a phase transition at extreme densities, turning into a region dominated by dark energy, a vacuum energy with negative pressure, like the cosmological constant driving cosmic acceleration. This interior vacuum pushes outward, while the star's outer layers push inward, balancing perfectly at a thin, ultra-dense shell. The result? From the outside, a gravastar looks almost exactly like a black hole. Light bends around it. Its radius hovers near the Schwarzschild radius. But inside, no singularity forms. Instead, spacetime transitions smoothly from normal matter through the shell into a dark energy core where pressure equals negative density. Mathematically, this avoids infinite curvature because the interior never collapses completely. In a way that is similar, dark stars work, but they often use quantum gravity forces. Some models say that when matter falls apart toward what classical relativity calls a singularity, quantum gravity kicks in at almost Planck densities. This makes an extremely dense object that doesn't have an event horizon, a singularity, or even a physical surface. Matter that is falling can sometimes bounce back at microscopic levels, creating what are sometimes called Planck stars. These stars release their stored energy over eons of time, which could connect black hole evaporation to gamma-ray bursts or other cosmic signs. Gravastars and dark stars both have the same main idea. Singularities and classical event horizons may be mistakes that happen when you don't take quantum effects into account. In full quantum gravity, spacetime might have separate structures or new pressure sources that stop it from collapsing into infinity, similar to how neutron degeneracy pressure stops the collapse of white dwarfs before they collapse into infinity. From the outside, distinguishing these exotic interiors from true black holes proves difficult. Gravastars can mimic black holes so closely that only subtle signals, like gravitational wave echoes after mergers, might reveal differences. If two gravastars collide, their lack of horizons could let gravitational waves bounce inside before escaping, producing secondary echo pulses absent in ordinary black hole mergers. LIGO and Virgo have searched for such echoes in detected events. So far, results remain inconclusive, but improved detectors might test these ideas soon. Hawking radiation is another thing that might give us a sign. Because boundaries let quantum effects split particle pairs near the edge, true black holes slowly disappear through heat. Since nothing ever goes away behind an absolute horizon, gravitas stars that don't have horizons wouldn't spread in the same way. This could mean that the information paradox isn't even a problem. Some dark star models go even further and say that the insides are made of strange states of matter like Bose-Einstein condensates in which particles share a single quantum state at the macro level. Others use asymptotically safe gravity or string theory fixes that change Einstein's equations at high curvature and automatically stop singularities from forming. In these cases, matter that is collapsing reaches an extremely high but limited density before new physics stops it from compressing any further, leaving behind a stable, compact residue. Cosmology even offers parallels. The Big Bang's singularity itself might vanish in quantum cosmology, replaced by a bounce from a prior contracting phase. Gravastars and dark stars apply similar reasoning to gravitational collapse. When densities approach Planck scales, quantum geometry or vacuum energy creates repulsive pressure balancing gravity's pull. There are still problems. Gravastar shells need strange equations of state that don't work for any known matter, like negative pressure or tension. Stability studies show that when things get messed up, some configurations fall apart into black holes, while others explode outward. A lot of the time, dark star models depend on quantum gravity effects that haven't been proven by experiments. Until studies show that these things don't behave like classical black holes, they will stay hypothetical. Still, the drive stays strong because singularities show that physics isn't complete. Most scientists think that quantum gravity will resolve them in some way. It's still not clear whether the resolution will look like gravastars, dark stars, or something completely different. Quantum foam at subplanck scales. When seen through human eyes, reality seems smooth and dull. Light rays follow steady paths, rulers accurately measure distances, and planets move in beautiful circles. When you look very close, past atoms, nuclei, and even quarks, science suggests that there is a point where this smoothness disappears totally. Spacetime might not look like a continuous cloth at all when it gets close to the Planck length, which is about 1.6 times 10 to the power of minus 35.5 meters. It might instead shake and flicker like the water when it's stormy. John Wheeler, a physicist, came up with the word quantum foam to describe this crazy, made-up sub-Planck world, where even geometry is filled with quantum uncertainty. Why suspect such chaos exists? Because two pillars of modern physics demand it. General relativity treats spacetime as continuous, curving smoothly under mass and energy. Quantum mechanics, by contrast, says fields at tiny scales fluctuate violently thanks to the uncertainty principle. The smaller the region, the larger the energy fluctuations allowed. Bring these together, and spacetime at the tiniest scales must jitter, warp, and possibly even change topology moment to moment. Distances, times, even causal order might lose fixed meaning below the Planck scale. When you put together the basic principles of nature, you can't avoid these changes in math. When you divide h bar times g by c cubed, you get L sub p, which is the Planck length. When you divide L by c, you get T sub p, which stands for Planck time. When you get to these sizes, the energy density from quantum changes is so high that reality bends very badly. When there is quantum uncertainty, the smooth geometry that general relativity describes falls apart. This leaves behind a frothy space-time foam, where normal ideas like a single place in space or a single instant in time don't make sense. What might quantum foam actually look like? No one knows for sure, but theories paint vivid possibilities. Tiny virtual black holes could form and evaporate constantly as energy fluctuations briefly exceed the density needed to pinch off microscopic horizons. Wormholes might flicker into existence at sub-Planck scales, connecting distant regions through ephemeral tunnels before vanishing again. Space-time topology itself, the connectivity of points, might change repeatedly, producing a seething network of quantum bubbles rather than a single smooth manifold. This foaminess would remain hidden at larger scales because quantum fluctuations average out over distance and time. Just as a rough sea looks flat from high altitude, space-time smoothed over many Planck lengths recovers the continuous geometry Einstein described. But probe scales near 10 to the negative 35 meters, and quantum foam might dominate, replacing curves and geodesics with something fundamentally discrete or probabilistic. Several approaches to quantum gravity try to capture this picture mathematically. Loop quantum gravity models space-time itself as a network of finite loops or spin networks, giving areas and volumes discrete spectra rather than continuous values. At Planck scales, geometry becomes granular. Space consists of finite quanta, stitched together dynamically. String theory offers a different view. Fundamental strings or higher dimensional branes replace point particles, smearing interactions over finite lengths that tame quantum fluctuations before singularities form. Strings vibrating in multiple dimensions might prevent infinite curvatures by spreading energy out across minimal sizes, avoiding the worst infinities plaguing classical gravity. Other possibilities use causal dynamical triangulations, which build spacetime from small separate building blocks that are statistically stuck together, or asymptotic safety, which says that at high energies, gravity's strength approaches a fixed point, which softens quantum changes enough to keep physics predictable. Quantum foam remains elusive because Planck scales lie absurdly far beyond direct experimental reach. Particle accelerators like the Large Hadron Collider probe down to about 10 to the negative 19 meters, 16 orders of magnitude larger than the Planck length. Testing quantum foam directly would require energies near the Planck energy, about 10 to the 19th giga-electron-volts, hopelessly beyond current technology. Someday, though, hints that aren't direct might show up. Lorentz invariance is nature's symmetry of space and time. If space-time has a separate structure at very small scales, it could cause tiny violations of Lorentz invariance, which changes how high-energy photons move over billions of light-years. Gamma-ray bursts and blazar flares may have energy-dependent arrival times that show how they interact with quantum foam along the way. At least up to now, observations have shown that these kinds of effects are very limited. This means that any foaminess keeps Lorentz symmetry almost entirely. Gravitational wave detectors might help too. If spacetime jitters quantum mechanically, perhaps faint spacetime noise hides in interferometer signals like those from LIGO or Virgo, though disentangling such noise from instrument backgrounds remains daunting. During the universe's first moments, near the Planck time of 5.4 times 10 to the negative 44 seconds, quantum foam might have left imprints on primordial gravitational waves or density fluctuations later stretched across cosmic scales by inflation. Future probes of the cosmic microwave background's polarization or space-based gravitational wave observatories like LISA could, in principle, test whether quantum fluctuations of spacetime itself shaped the earliest cosmos. Tachyonic fields in high-energy theories. When it comes to imagined creatures that live in theoretical physics, tachyons are some of the most interesting and confusing. They are made up of particles or fields with imaginary mass that, at least theoretically, move faster than light. According to standard relativity, nothing with real positive mass can speed up to or past the speed of light, because it needs more and more energy as it gets closer to the cosmic limit c. This doesn't make sense when it comes to tachyons, because the numbers show they can't slow down below the speed of light. If they exist, they always move faster than light, which goes against the laws of physics and makes them unstable. The energy-momentum relation in special relativity is E squared equals P squared times C squared plus M squared times C to the fourth. Here, E is the energy, P is the momentum, M is the rest mass, and C is the speed of light. For ordinary particles with real positive mass, this guarantees that E squared is always positive and real. But imagine if M squared were negative. That would make the mass imaginary, written as M equals I times mu, where mu is real. The equation then becomes E squared equals P squared times C squared minus mu squared times C to the fourth. For small values of momentum P, the right-hand side becomes negative, which would make energy imaginary, something that doesn't make sense physically. But for large enough momentum, the energy stays real. In that case, the particle's speed must always be greater than c, the speed of light, because trying to slow it down below light speed would require infinite energy. When the current state of a system is on top of an unstable potential hill, quantum field theory can create tachyonic modes. Early studies showed a tachyonic mass term for the Higgs field. This didn't mean that particles were moving faster than light, but that there was an instability. Normal particles with real masses came out of the field after the symmetry broke as it rolled down into a stable vacuum. In this way, tachyons don't always mean strange messages that travel faster than light. Instead, they often mean stages that are about to change into something stable. String theory also met tachyons early in its history. The simplest bosonic string models produced tachyonic ground states, suggesting the vacuum itself was unstable. Only with supersymmetry and more sophisticated formulations did stable, tachyon-free string theories arise, forming the basis for modern string model building. But what if physical tachyons really existed? Their superluminal speeds threaten causality, the principle that causes precede effects. In relativity, faster-than-light signals let observers in different frames disagree about time order. One observer's effect becomes another's cause, enabling paradoxes, like sending information into your own past. Because of this, most scientists don't believe in real spreading tachyons. This is enforced by stability and unitarity in quantum field theory. Negative mass-squared terms mean either imagined energies or the vacuum breaking down very quickly and badly. Theories that make sense either get rid of tachyonic states by breaking symmetry, like the Higgs, or see them as math errors instead of real particles. Yet some exotic models keep playing with the idea. Certain versions of Lorentz-violating theories, where relativity's speed limit isn't absolute, explore superluminal excitations without paradoxes because preferred reference frames break the symmetry, causing causal loops. K-essence models in cosmology sometimes allow field perturbations traveling faster than light relative to cosmic expansion without letting information signals form closed time-like curves. Even so, such scenarios remain speculative, tightly constrained by observations showing relativity works extremely well across astrophysics and particle physics. Could tachyon-like phenomena appear astrophysically? Hypothetical superluminal neutrinos briefly made headlines in 2011 when the OPERA experiment reported neutrinos apparently exceeding light speed by parts per 100,000. Later checks found experimental errors, loose cables, faulty timing equipment, erasing the anomaly. Subsequent experiments confirmed neutrinos obey relativity's speed limit perfectly. Astronomers also thought about tachyons because very fast particles don't always follow the rules for how much energy they can have. For example, the Greisen-Zatsepin-Kuzmin GZK limit says that particles should lose energy when they combine with cosmic microwave background photons. Some scientists thought that these events might be caused by tiny Lorentz violations or strange particles, but new data showed that they were more likely to be caused by normal physics and didn't need superluminal messages. False vacuum bubble interiors. The void of space, which has the least amount of energy, is thought to be steady by quantum field theory. What if it's not, though? What if the thing we call empty space is actually just metastable, and sitting on a local energy minimum? The universe would then be living in a fake vacuum, and quantum tunneling could one day cause a terrible phase change into a real vacuum with less energy density. The edge of this new area, which would be a bubble of pure vacuum, would grow at almost the speed of light, changing the rules of physics inside its walls. This isn't science fiction. It emerges naturally in many quantum field theories. Fields can have potentials shaped like valleys and hills. Our universe may sit in a valley, a vacuum state, that isn't the absolute lowest one available. Quantum mechanics allows tunneling through the energy barrier, separating it from a deeper valley. If a bubble of true vacuum ever nucleates via tunneling, it grows relentlessly because the new vacuum's lower energy density acts like negative pressure, pulling the bubble wall outward at ultra-relativistic speeds. Inside the bubble, physics itself changes. Particle masses, coupling constants, even the number of stable particles could differ entirely if the Higgs field or other fundamental fields settle into new expectation values. At the bubble wall, enormous energy from the difference between false and true vacuum densities converts into a searing shell of particles and radiation sweeping outward. For anything inside the bubble, the transition proves unsurvivable because chemistry, nuclear physics, and atomic structure all depend on vacuum parameters that might shift catastrophically. Calculations of vacuum decay use semi-classical methods pioneered by Sidney Coleman in the 1970s. The tunneling rate depends exponentially on the action of a bounce solution, a configuration describing the field slipping through the energy barrier to form a critical bubble just large enough that expansion lowers its energy rather than shrinking it back to nothing. Once nucleated, the bubble wall accelerates outward, approaching light speed as energy differences convert into kinetic energy of expansion. Could this really happen in our universe? Measurements of the Higgs boson mass around 125 giga-electron volts and the top quark mass near 173 giga-electron volts suggest our electroweak vacuum may indeed be metastable, rather than absolutely stable when extrapolating the standard model to high energies. At enormous scales near 10 to the power of 11 giga-electron volts, the Higgs potential might dip below the value at our vacuum, creating the possibility, however remote, of decay to a lower energy state. Inside the bubble, physics depends on the details of the true vacuum. If fundamental constants shift, atoms might not form, protons could decay rapidly, forces binding nuclei together might vanish or strengthen catastrophically. Space itself might expand or contract differently under the new vacuum's energy density, possibly triggering rapid gravitational collapse or inflationary expansion. Either way, life and our familiar universe would not survive the passage of the bubble wall. Cosmologists are interested in the bubble's inside shape because it links quantum field theory to general relativity. In a real vacuum, the energy density is like a cosmic constant. Positive values speed up growth like dark energy, and negative values make spacetime collapse into a big crunch. In some cases, loops of vacuum decay go through different energy levels, making a multiverse where different parts of space settle into different vacuums with their own set of physical rules. From what we can see, there are no signs of vacuum decay. After inflation stopped, there is no sign of bubble impacts or phase changes in the cosmic microwave background. Particle colliders like the Large Hadron Collider don't have enough energy to cause decays, because bubble nucleation relies on quantum tunneling across the whole void, not just local energy accumulation. Even astronomical disasters like supernovae don't create the right conditions for new bubbles to form. Big rip singularities from phantom energy. These days, the world is expanding faster and faster thanks to something unknown called dark energy. Dark energy was found in 1998 by looking at supernovae far away. It acts like a fluid with negative pressure, pushing space-time apart instead of pulling matter together. In Einstein's equations, it functions as a cosmic constant, a level of energy that fills all space and is not changed by the expansion of the universe. If this constant stays the same, The speed of light in space will keep increasing forever, pushing galaxies farther away until in the far future, only cold, empty space is left. What if dark energy doesn't stay constant, but actually grows stronger with time? To describe this, physicists use something called the equation of state parameter, W. It's the ratio of pressure to energy density. A true cosmological constant has W equal to -1. Ordinary matter has W equal to 0, and radiation has W equal to 1/3. If W is less than -1, we enter the realm of phantom energy, and phantom energy drives one of the most dramatic fates possible for the universe, the Big Rip. Here's the idea. Normally, as the universe expands, energy densities thin out. Matter spreads as 1 over the scale factor cubed, radiation as 1 over the scale factor to the 4th. Even regular dark energy with W equal to -1 stays constant per unit volume, which means as space grows, dark energy eventually dominates. Phantom energy is different. With W less than -1, its energy density actually increases as the universe expands. The more space grows, the stronger phantom energy gets, because its negative pressure pumps energy into expansion itself. This runaway effect forces the universe to expand faster and faster, until the scale factor blows up to infinity in a finite time. That final singularity is the Big Rip. As the rip approaches, destruction unfolds in stages. Billions of years before the end, galaxy clusters drift apart. Later, stars escape their galaxies. Solar systems unravel as orbits can't keep up with expansion. Near the very end, planets are torn apart, then molecules, then even atoms. Finally, space-time stretches so violently that not even the nuclear force can hold matter together. Everything dissolves into an ever-thinning sea of particles before time itself ends. The math comes from solving the Friedmann equations with W less than -1. The time left until the rip is given by T sub rip minus T naught equals 2, divided by 3 times the absolute value of 1 plus W times H naught. Here T naught is today's time and H naught is the Hubble constant. If W is only slightly below -1, the rip lies tens of billions of years away. If it's more negative, it could come sooner, though still far beyond any timescale we need to worry about. Right now, observations put W extremely close to -1, matching a cosmological constant, but not completely ruling out phantom energy. Data from the Planck satellite, supernova surveys, and baryon acoustic oscillations all suggest W equals -1 plus or minus about 0.05. That means the Big Rip isn't confirmed. It would require W truly less than -1, measured with very high precision. In relativity, phantom energy also breaks the basic rules of energy. The null energy condition says that the sum of the energy density and the pressure should not be negative. If W is less than -1, that condition doesn't work because the negative pressure is stronger. In theory, once something is broken, strange things can happen, like spacetimes that can be driven by warp drives or wormholes that can be passed through. But in most true models, these kinds of fluids are very unstable. Some ideas say that ghost energy isn't even real matter but rather a result of changing gravity. As an example, F of R gravity or brane world models can act like W less than -1 without adding fluids with unstable negative energy. Some people think that dark energy and dark matter might behave in a way that changes over time. If a Big Rip is truly ahead of us, we might see warning signs long before. Precision galaxy surveys that map distances and expansion rates could reveal W drifting below -1. Future missions like Euclid, the Nancy Grace Roman Space Telescope, and CMB-S4 are designed to measure W with percent-level accuracy, which could either rule out phantom energy or confirm that the most violent ending awaits our universe. Pre-collapse neutron star core phases. When a big star runs out of nuclear fuel, the pressure from fusion that kept gravity in check goes away. The star's core falls apart under its own weight, which causes a supernova explosion. If the mass is high enough, a black hole may form in its place. But in the moments before the point of no return for collapse, the core turns into a laboratory for very dense matter with pressures and densities that are on par with anything else in the universe. These neutron star cores that are about to break look into stages of matter that regular neutron stars and even particle accelerators can't reach. This pushes the limits of what we know about physics. To see why, let's begin with an ordinary neutron star. These objects form when the remains of a massive star collapse in a supernova, but stop short of becoming a black hole. A neutron star squeezes 1 to 2 times the mass of the Sun into a ball only about 20 kilometers across. Its outer crust is made of neutron-rich atomic nuclei packed together inside a sea of electrons. Deeper in, the nuclei dissolve, leaving behind a strange fluid of superfluid neutrons mixed with a few protons and electrons to balance the charge. At densities above nuclear saturation, about 2.8 times 10 to the 14th grams per cubic centimeter, matter behaves in ways completely unlike anything we can find on Earth. But star cores that are falling can go beyond these limits before the horizons form. During collapse, as mass builds up inside, temps soar past tens of MeV, hundreds of billions of kelvins. Densities rise several times above nuclear saturation, and nucleons are pushed into new states of matter. Physicists think that in the last few seconds before a black hole forms, whole phases other than neutrons may appear briefly. A possible cause involves hyperons, which are particles that have weird quarks, along with the up and down quarks that are found in protons and neutrons. When the levels are high enough, making hyperons may lower the system's energy by swapping normal nuclear matter with a soup full of hyperons. But hyperons also weaken the equation of state, which is the relationship between mass and pressure. This makes it easier for the star to be compressed. If there are too many hyperons, the star falls apart faster, which goes against what we know about neutron stars with masses greater than 2 solar masses. This softening must be stopped at very high densities by something, like hyperon forces that push things away or changes to even harder quark matter. Meson condensates are another option. When densities get high enough, particles like pions and kaons that act as mediators between nuclear forces might form collective quantum states that fill the core with Bose-Einstein condensates. These condensates might change the rates at which neutrinos cool, how they spin, and the point at which they collapse. If these changes are found by future devices, they could leave marks on supernova neutrino bursts or gravitational waves. Such phases could temporarily halt collapse if pressure stiffens again at higher densities, perhaps creating hybrid stars with quark cores and nuclear mantles. Some equations of state even allow a separate family of quark stars distinct from neutron stars and black holes, though evidence remains speculative. The neutrino burst from supernova 1987A carried information from deep inside a collapsing core, hinting at extreme densities, but revealing little detail about phases reached before black hole formation. Future galactic supernovae observed with detectors like Hyperkamiokande or Dune could record thousands of neutrinos, mapping cooling rates sensitive to exotic matter phases in the milliseconds after collapse. Gravitational waves provide another window. Asymmetric collapse or phase transitions inside the core could produce brief, intense gravitational wave bursts detectable by LIGO, Virgo, or next-generation detectors like the Einstein telescope. A sharp softening of the equation of state, for instance, might trigger characteristic frequency changes in the wave signal as the core contracts or fragments. Numerical simulations explore these regimes using relativistic hydrodynamics, nuclear physics equations of state, and neutrino transport, but uncertainties about hyperon interactions, quark matter properties, and condensate phases remain huge. Laboratory experiments at heavy ion colliders like RHIC and LHC recreate quark-gluon plasma at high temperatures but low densities, opposite of cold, dense supernova cores. Astrophysical observations thus remain our best hope for probing matter at extremes unreachable on Earth. Relativistic jet launch regions near supermassive black holes. The relativistic jets that come from the centers of busy galaxies are one of the most interesting and exciting things that can happen in space. Huge beams of plasma shoot out from areas near supermassive black holes that are millions or billions of times the mass of the Sun. They speed up particles to almost the speed of light and cover hundreds of thousands of light years. Some of them are so bright in X-rays, radio waves, and gamma rays that they can be seen from other galaxies. But the science behind how they were born is still one of the biggest puzzles in astrophysics. It involves magnetic fields, plasma physics, relativity, and maybe even quantum effects, all coming together in places where gravity bends space and time. The story begins in the accretion disk, swirling around a supermassive black hole. Gas falling toward the black hole doesn't plunge straight in. It carries angular momentum, forming a disk of orbiting plasma, heated to millions of degrees as turbulence, magnetic fields, and viscosity dissipate gravitational energy. This disk radiates across the electromagnetic spectrum, powering quasars and active galactic nuclei that outshine their host galaxies. There are, however, systems above and below this circle that send out jets, which are narrow, collimated beams that speed outward at relativistic speeds and carry energy, mass, and magnetic flux into space beyond our galaxy. The jet power often matches or beats the brightness of the accretion disk, which means that energy is being taken out of the black hole system very efficiently. But where did it come from? Two main mechanisms dominate theoretical models. The first, the Blandford-Znajek process, 1977, taps the black hole's own rotational energy. A spinning black hole drags spacetime around it through frame dragging, especially inside the ergosphere where no object can remain stationary relative to distant observers. If magnetic field lines thread the horizon, frame dragging twists them, inducing electric currents that extract rotational energy electromagnetically, launching pointing flux-dominated jets outward. In essence, the black hole acts like a unipolar inductor, a cosmic dynamo converting spin into jet power. The second mechanism, the Blandford-Payne process, 1982, instead taps the accretion disk's rotational energy. Magnetic fields anchored in the disk fling material outward centrifugally along open field lines if they tilt at less than 60 degrees from the disk surface. Gas moves along these rotating field lines like beads on a wire, accelerating outward until magnetic pressure and hoop stresses collimate the flow into narrow jets. Both processes likely operate together in many systems. The disk launches winds and outflows, while the black hole's spin powers the most relativistic, tightly collimated inner jets. General relativistic magnetohydrodynamic (GRMHD) simulations now model these environments with remarkable realism, showing magnetic fields threading the horizon, jets accelerating and collimating over hundreds of gravitational radii, and turbulence in the disk regulating mass accretion rates feeding the engine. Jet speeds measured by very long baseline interferometry, VLBI, often show apparent superluminal motion, an optical illusion from relativistic effects when jets point nearly along our line of sight. True bulk Lorentz factors reach 10 or higher, meaning material moves at over 99.9% of light speed. Shocks within the jets accelerate particles to extreme energies, producing synchrotron radiation in radio waves and inverse Compton scattering generating X-rays and gamma rays. Jets feedback also changes the framework of the universe. When jets hit intergalactic gas, they make radio lobes bigger, which can be seen in giant radio galaxies. They also heat up the area around clusters and keep star formation in check by stopping huge galaxies from cooling down too much. This AGN feedback connects the growth of black holes to the development of galaxies. It explains connections like the M-sigma relationship between the mass of a black hole and the spread-out speed of stars in galactic bulges. Blazars are galaxies that have jets that are directed almost directly at Earth. They have been found to give off neutrinos, which suggests that there are more than just simple electron processes going on. They think that hadronic processes, which involve protons and larger particles, might be going on at the same time as electronic waves. This could be a link between these jets and the sources of very high-energy cosmic rays, which have energies above 10 to the 18th electron volt. Also, blazar jets would be places to study particle astronomy at energies much higher than what we can reach on Earth. This would make them labs for plasma physics and relativity. Cosmic filament shock regions. The big picture layout of the universe is not at all like the smooth, even universe we might imagine from afar. Instead, galaxies form groups along filaments, which are huge, thread-like structures that stretch hundreds of millions of light-years across the universe. At dense points where these strands meet, galaxy clusters can be found. In between them, huge empty spaces are almost devoid of matter. Filaments aren't just quiet roads in galaxies, though. Space between galaxies is shaken by cosmic shock waves that heat plasma, speed up particles, and shape the biggest structures in the universe, with physics as powerful as anything near black holes. The story begins after the Big Bang, when matter filled space almost uniformly, but with tiny density fluctuations seeded by quantum processes during inflation. Over billions of years, gravity amplified these fluctuations. Slightly denser regions attracted more matter, growing into sheets, filaments, and nodes, while emptier regions expanded into voids. Dark matter provided the scaffolding. Baryonic gas and galaxies followed its gravitational blueprint, forming the cosmic web we map today with galaxy surveys, like the Sloan Digital Sky Survey, and simulations like Illustris and Millennium. As gas flowed along filaments toward clusters, it reached supersonic speeds relative to the surrounding medium. Where converging flows met or gas slammed into growing structures, enormous collisionless shocks formed, converting kinetic energy into heat, turbulence, and cosmic rays. These shocks extend for tens of megaparsecs, dwarfing any structures inside galaxies or clusters. Unlike shocks in air or water, collisionless shocks arise in plasma, where particles rarely collide directly. Instead, electromagnetic fields and collective plasma effects mediate energy dissipation. At filament shocks, magnetic fields, though weak compared to those in galaxies, grow through instabilities and turbulence, guiding charged particles into repeated crossings of the shock front. Each crossing accelerates particles via the Fermi process, producing cosmic rays with power law energy spectra, similar to those from supernova remnants, but on far larger scales. The hottest gas in the universe is found in these regions. As matter falls into cosmic filaments and galaxy clusters, shock waves heat it to between 100,000 and 10 million kelvins. This creates what scientists call the warm-hot intergalactic medium, or WIM, which may contain a large share of all the normal matter, or baryons, in the universe today. Detecting the WIM is difficult because its X-ray and ultraviolet glow is very faint, but astronomers can trace it indirectly, through absorption lines in the light of distant quasars and through the Sunyaev-Zeldovich effect, where cosmic microwave background photons are scattered by the hot gas. Some of the largest particle accelerators in the cosmos may be these filament shocks. Radio observations already detect radio relics, giant polarized synchrotron sources tracing shock fronts at cluster edges, where electrons spiral along amplified magnetic fields after shock acceleration. The sausage and toothbrush relics in merging galaxy clusters stretch for millions of light-years, glowing in radio waves as cosmic ray electrons emit synchrotron radiation. Gamma-ray telescopes like Fermi LAT search for high-energy photons from cosmic ray protons colliding with gas in filaments, though detections remain tentative because densities stay low compared to galaxies. Neutrino observatories like IceCube might eventually test whether the highest energy cosmic rays partly originate in these megaparsec scale shocks rather than only in active galactic nuclei or gamma-ray bursts. You can also change how groups grow with filament shocks. As gas builds up along filaments, outer accretion shocks heat it up before it meets the medium inside the cluster. When two clusters join, they create even stronger merger shocks. These shocks create the brightest radio relics and speed up cosmic rays to levels that are much higher than what humans can achieve with reactors like the Large Hadron Collider. Numerical models show complex structures, including bow shocks in front of subclusters coming in, turbulent wakes behind them, and sheet-like shocks following the ends of filaments that feed the clusters. Even though they started out as almost zero magnetic fields in the early universe, magnetic fields get stronger through turbulence and dynamos until they hit micro-Gauss strengths. It's still not clear how these fields formed, from quantum fluctuations in the beginning, battery effects, or streams from space, which is related to astronomy, plasma physics, and the history of galaxies. Mapping filament shocks pushes current instruments to their limits because emissions stay faint and extended. Next-generation radio arrays like the Square Kilometre Array, SKA, will trace synchrotron radiation from cosmic ray electrons across megaparsec scales with unprecedented sensitivity. Future X-ray missions like Athena will map WIM gas through absorption and emission lines, revealing how shocks heat intergalactic plasma. Magnetospheric gap acceleration zones. Some of the most powerful particle accelerators in the universe don't sit in galaxy clusters or giant filaments. They exist in the tiny magnetospheres of neutron stars, pulsars, and magnetars. These compact objects are only a few tens of kilometers across, yet their magnetic fields can reach up to 10 to the 15th Gauss, and they spin anywhere from once every few seconds down to once every millisecond. As they rotate, they drag their magnetic fields with them, generating colossal electric fields. These fields can rip particles off the star's surface, fling them to near-light speeds, and launch winds, radiation beams, and possibly even high-energy cosmic rays. Magnetospheric gaps are the main idea. These are places where there aren't enough charges to cancel out the electric fields that the star's spin makes. The atmosphere of a pulsar is usually full of plasma. Then, the charges move around to cancel out the parallel electric fields that run along the magnetic field lines. What's left are the orthogonal components, which push the particles outward without using any force. But if the density of the plasma falls below what is known as the Goldreich-Julian density, holes appear. This is the lowest density needed to cancel out those fields. Inside these gaps, particles feel the full brunt of unscreened electric fields running along the magnetic field lines. Electrons and positrons accelerate to Lorentz factors of 1,000,000 or more, blasting out gamma rays as they follow curved magnetic paths, a process called curvature radiation, or by boosting low-energy photons in inverse Compton scattering. Those gamma rays can then create new electron-positron pairs, either in strong magnetic fields or by colliding with other photons. This cascade fills the magnetosphere with fresh plasma and fuels the powerful winds and beams of radiation we see from pulsars and magnetars. Different models describe where these gaps form. Polar cap models place them near the magnetic poles, where open field lines stream outward beyond the light cylinder radius, the distance where correlation with the star would require light-speed motion. Slot gap and outer gap models locate them higher in the magnetosphere along last open field lines, or near the null charge surface where the Goldreich-Julian density changes sign. In all cases, gaps act as linear accelerators, converting rotational energy into beams of radiation and particles. Light curves and spectra from gamma-ray pulsars seen by telescopes like Fermi LAT support outer magnetosphere emission. This is because they fit forecasts of where curvature radiation from ultra-relativistic particles dominates above a few giga-electronvolts. Some pulsars send out pulsed gamma rays with energies higher than 100 giga-electronvolts. These rays make simple curved models hard to understand and point to other processes, such as inverse Compton scattering in magnetospheric regions that are farther out than the light cylinder in pulsar winds. Magnetars take these processes to an even higher level because their magnetic fields are stronger than the quantum critical field of 4.4 times 10 to the 13th Gauss. At this strength, quantum electrodynamics predicts exotic effects like vacuum birefringence, where empty space acts like a crystal, and photon splitting, where one gamma-ray photon can break into two lower-energy photons. In a magnetar's magnetosphere, magnetic stresses twist the field lines until they snap and reconnect violently. The result is a giant flare, blasting energy in soft gamma rays and hard X-rays. During these events, magnetospheric gaps may briefly surge with electric fields strong enough to accelerate particles to even higher energies before new pair cascades fill the gaps and shut the process down. Pulsar wind nebulae, such as the Crab Nebula, show us the aftermath of this kind of acceleration. The crab's central pulsar spins once every 33 milliseconds and loses rotational energy at about 5 times 10 to the 38th EOGs per second. Most of that energy doesn't come out as pulsed light, but instead as a relativistic wind of electrons, positrons, and magnetic fields streaming out from magnetospheric gaps and the light cylinder region. When this wind slams into the surrounding supernova debris, it creates a termination shock. At that shock, particles are accelerated once again, producing the Crab Nebula's famous synchrotron glow, which shines across the spectrum, from radio waves to visible light, and all the way up to X-rays and gamma rays. Gap acceleration also appears in black hole magnetospheres if magnetic fields thread spinning horizons. In low-density environments around supermassive black holes, unscreened electric fields near the poles could accelerate particles to ultra-high energies, powering TeV gamma ray emission from systems like M87 or Centaurus A. Here, gaps form because pair production from ambient photons cannot supply enough plasma to short out electric fields, mimicking pulsar-like acceleration on much larger scales. Axion photon conversion regions. The Axion is one of the most fascinating proposals in the search for physics beyond the standard model. It is an imaginary, very light particle that was first suggested in the late 1970s as a way to solve the strong CP problem in quantum chromodynamics, QCD. This puzzle asks why the strong nuclear force seems to follow charge parity symmetry a lot more than we would expect, since quantum field theory allows for small breaks. Axions came about naturally as a solution. Their presence pushes QCD to change these mistakes all the time. But axions, and broader axion-like particles, or ALPs, carry another potential superpower. They interact extremely weakly with matter, yet couple faintly to electromagnetic fields. In strong magnetic environments, axions can convert into photons and vice versa through the Primarkov effect. That means regions with intense magnetic fields, like neutron star magnetospheres, supernova remnants, or galaxy clusters, could act as cosmic laboratories, where axion photon conversion leaves observable signatures across radio, X-ray, and gamma-ray bands. Axion-photon interactions add a new term to the physics equations. It is written as G sub a gamma gamma times a times E dot B. There is an axion field called A, an electric field called E, and a magnetic field called B. The axion field is denoted by G sub a gamma gamma. In a magnetic field in the background, this term mixes axions and photons so that some can change back and forth as they move, like neutrinos change between different types. This change is more likely when there are bigger magnetic fields, larger areas, and higher photon energies. It is less likely when the axion is denser. Astrophysicists use this effect to hunt for axions in several ways. First, stellar cooling anomalies. If axions exist, they could escape directly from stellar cores, carrying away energy. This would change how stars age and shine, altering the lifetimes or brightness of red giants, white dwarfs, or neutron stars. Observations of white dwarf cooling and the neutron star in Cassiopeia have led to debates about whether axions might explain the extra cooling seen beyond what neutrinos account for. Second, supernova 1987A. The neutrino burst from this supernova set strong limits. If too much energy had leaked out in axions, the neutrino signal would have been shorter than what was observed. This already rules out some axion models with couplings that are too strong. Third, X-ray and gamma-ray transparency. Very high energy gamma rays from distant blazars sometimes arrive at Earth more easily than expected, even though interactions with background light should block them. One idea is that some photons convert into axions near the blazar, travel across space untouched, and then convert back into photons inside the Milky Way's magnetic field. This would make the universe look more transparent than standard physics predicts. Instruments like Fermi LAT, HESS, and future observatories such as CTA look for these irregular patterns in blazar spectra. Fourth, galaxy cluster magnetic fields. Clusters of galaxies contain magnetic fields stretching across millions of light years. X-ray light from active galactic nuclei shining through these regions can show tiny spectral wiggles caused by Axion photon conversions. Detecting or ruling out such patterns helps constrain Axion masses and couplings in ways complementary to lab experiments. Fifth, neutron star magnetospheres. With fields as high as 10 to the 15th Gauss, neutron stars and magnetars are perfect environments for Axion conversion. Radio telescopes watching pulsars or magnetars might catch unusual polarization patterns or extra emission if axions streaming from inside the star flip into photons in the surrounding field. Axion photon conversion also has cosmological consequences. Extremely light axions, with masses around 10 to the minus 22nd electron volts, behave as fuzzy dark matter, smoothing out small-scale cosmic structures. Heavier axions could still make up part of dark matter and leave traces in the cosmic microwave background or in galaxy clustering. Axions should easily show up in string theory, according to theory. A lot of different light scalar fields, sometimes called the axiverse, appear when extra dimensions are squished together. Their masses cover a very large range. Some of these particles that look like axions may interact strongly enough with photons to be seen in astronomical observations, even if they are never found by colliders. Even new observations give us hints. A strange X-ray line near 3.5 kilovolts was seen in data from galaxy clusters and the Milky Way. This led to the idea that dark matter might be breaking down, or axion-like particles might be changing in the magnetic fields of clusters. Later research called the line into question, but new X-ray projects like XRISM and Athena will look again with a lot more detail. Magnetic monopole plasma interactions. As we know it, magnetism always comes in pairs. A north pole pulls along a south pole. This is true for bar magnets, spinning electrons, and planetary dynamos. When you cut a bar magnet in half, each half gets a new north and south end. The poles stay matched no matter how small you get. But scientists have long wondered, what if there are magnetic monopoles? These are particles that have a single north or south magnetic charge, which is like an electric charge, but for magnets. Their find would change the field of physics by rewriting Maxwell's equations and showing how electric charge quantization works. It could also give cosmic plasmas completely new behaviors at astrophysical scales. The idea dates back to Paul Dirac in 1931. Dirac showed that if even a single magnetic monopole exists anywhere in the universe, it would explain why electric charge comes in discrete, quantized units rather than arbitrary values. The presence of one monopole imposes consistency conditions on quantum wave functions that force electric charge to be an integer multiple of a fundamental constant, an elegant link between electromagnetism and quantum theory. Later, theories called Grand Unified Theories, GUTs, said that the strong, weak, and electromagnetic forces all combine at very high levels to form a single force. As a result of breaking symmetry in the early universe, these ideas easily explain how magnetic monopoles formed as topological flaws. The universe cooled down, and the forces began to separate. Magnetic flux lines may have become trapped, leaving behind pointy remnants with a net magnetic charge. It would be very hard to speed them up or kill them if a lot of them were made. Each one would be very big, with a voltage of about 10 to the 16th gigavolts. As fossil records, they would be straight leftovers from the very beginning of time. Not a single monopole has shown up yet. Searches that have been going on for decades, using everything from old mica crystals that record particle tracks to detectors like Macro in Italy's Gran Sasso laboratory, have set very low upper limits on how common they are in the universe. Theorists now think that cosmic inflation slowed down any primordial monopoles to almost nothing by expanding space exponentially after they formed. This solved the problem of monopole overproduction that was present in early Gaia models. But if even a few remain in each galaxy or cosmic volume, their reactions with plasmas in space could show what they are. When monopoles move through cosmic magnetic fields, they would feel forces that are similar to electric charges in electric fields. They would follow the lines of the magnetic field and send out energy through electromagnetic interactions. In galaxy clusters, where magnetic fields run through plasmas on a megaparsec scale, monopoles would move due to magnetic Coulomb forces. This could create magnetically charged currents that change the behavior of the plasma in a way that is subtle but noticeable. In cosmic rays, a monopole crossing Earth's magnetic field would accelerate, gaining kinetic energy at a rate proportional to its magnetic charge times the local field strength. Extremely massive monopoles might reach relativistic speeds only over intergalactic distances, while lighter monopoles, if they exist, could produce ionization tracks or Cherenkov radiation in detectors like IceCube, Antares or Baikal GVD. Their signals would differ sharply from ordinary charged particles, because monopoles deposit energy continuously rather than in stochastic nuclear interactions, leaving smooth, bright trails in optical or radio detectors. Magnetic monopoles would also modify plasma physics fundamentally. In ordinary plasmas, electric charges create electric currents. Magnetic fields guide particle motion but arise only from moving electric charges or changing electric fields. Introduce magnetic charges, and Maxwell's equations become symmetric. Electric and magnetic charges mirror each other perfectly, each producing fields and currents of its own kind. Plasma waves would gain magnetic current analogues. Dual electric and dual magnetic alpha waves might propagate through intergalactic media. Magnetic reconnection, the process powering solar flares and magnetospheric storms, could gain entirely new channels if magnetic charges participate directly. Some thinkers even think about monopolium, which is made up of bound monopole-antimonopole pairs that are like electrons positron-positronium. If these states exist, they might not have any electric charge, but could break down into gamma rays with specific energies set by monopole masses and binding forces. In theory, gamma-ray telescopes like Fermi LAT or the soon-to-be-built Cherenkov Telescope Array, CTA, could find these kinds of annihilation lines coming from places where monopoles gather because of gravity, like galactic centers or galaxy clusters. Electron-positron pair plasma regions. Electrons mix with heavy, positively charged ions like protons or fully ionized nuclei in most plasmas in the universe, from the solar wind to the gas between galaxies. Its behavior is determined by the difference in mass between the electrons and ions. The electrons move quickly, carrying currents and reacting almost instantly to electric and magnetic fields, while the ions move slowly and make up most of the plasma's mass and inertia. In some of the universe's harshest environments, however, pair plasmas are made up of almost equal amounts of electrons and positrons, with no heavy ions present at all. These strange plasmas form when radiation levels, magnetic fields, or gravitational forces get so strong that matter and antimatter keep showing up together, destroying each other, and showing up again and again. This makes conditions that are not like any other astrophysical plasma. Pair plasmas differ fundamentally from electron-ion plasmas because electrons and positrons share the same mass but opposite charges. This symmetry erases the usual scale separation between light electrons and heavy ions, altering wave propagation, instabilities, and energy dissipation. In ordinary plasmas, electrons carry currents while ions supply inertia. In pair plasmas, both species respond equally fast, producing collective behaviors absent in any terrestrial laboratory except in brief, high-intensity laser experiments. Where do such plasmas show up naturally in the universe? First, pulsar magnetospheres. Rotating neutron stars with magnetic fields above 10 to the 12th Gauss create electric fields strong enough to rip charged particles off their surfaces. As these particles race along curved magnetic field lines, they emit gamma rays through curvature radiation, or by boosting lower energy photons in inverse Compton scattering. When the gamma ray energy goes above twice the electron rest mass, about 1.022 megaelectron volts, the photons can convert into electron-positron pairs through interactions with magnetic fields or nearby photons. This sparks dense pair cascades that fill the pulsar's magnetosphere with plasma streaming outward, powering pulsar winds and radio pulses. Second, Magnetar flares. Even stronger magnetic fields, above 10 to the 14th Gauss, surround magnetars. During giant flares, when magnetic reconnection or crustal quakes suddenly release huge amounts of energy in milliseconds, these fields trigger bursts of pair creation. A fireball of X-rays and gamma rays forms inside closed magnetic loops and quickly becomes an opaque electron-positron plasma before bursting outward. These events produce the brightest flashes of high-energy radiation ever seen outside our solar system, such as the 2004 flare from SGR 180620 that briefly outshone the entire Milky Way in gamma rays. Third, black hole coronae and jets. Near accreting black holes, hot coronae above the disk produce pairs when X-rays collide. Relativistic jets launched from the disk or the black hole itself may also carry electron-positron plasma across thousands of light years. Observations of polarization and radio emission from blazars and quasars suggest that in some cases, pairs dominate the jet's makeup, changing how it moves, stays stable, and radiates compared to jets filled with electrons and protons. Fourth, gamma-ray bursts. In the earliest fireball phase of a GRB, whether triggered by a collapsing massive star or emerging pair of neutron stars, conditions likely create a dense, radiation-filled electron-positron plasma. This fireball expands at near-light speeds, later converting its energy into the intense gamma-ray flashes that we detect across the universe. Physics in these environments differs sharply from familiar plasmas. For instance, alpha waves, magnetohydrodynamic oscillations where magnetic tension acts like a spring, propagate differently when both species share the same mass because charge separation effects vanish. Pair plasmas also suppress some drift instabilities common in ion-electron plasmas, while enhancing others unique to equal mass fluids. Relativistic temperatures complicate things further. When thermal energies rival or exceed rest mass energies, plasma pressure, inertia, and electromagnetic fields intertwine in fully relativistic magnetohydrodynamics (MHD) equations far beyond standard space or laboratory plasmas. Magnetic reconnection, the process converting magnetic energy into particle acceleration and heat, behaves differently too. In ordinary plasmas, heavy ions slow reconnection rates through Hall effects and ion inertial scales. Pair plasmas lack these scales, letting reconnection proceed rapidly, as seen in particle-in-cell (PIC) simulations, modeling pulsar magnetospheres and relativistic jets. Pair plasmas reveal themselves through annihilation radiation at 511 keV, the rest mass energy of electrons and positrons. The Milky Way's center glows in this line, detected by instruments like Integral, though whether pulsars, microquasars, or dark matter supply, the positrons remains debated. Gamma-ray bursts and blazar jets also show spectral cutoffs shaped by pair production and annihilation, regulating high-energy photon escape. By measuring polarization, we can learn more. Radio to X-ray emission from pulsar wind nebulae, jets, and GRB afterglows is mostly made up of synchrotron radiation from relativistic pairs spinning around magnetic fields. Some blazars have high polarization fractions, which suggests that pair plasma flows are guided by globally ordered magnetic fields on very large scales. In astronomy, pair plasmas may even be able to change how fast cosmic rays move. In pulsar winds, striped magnetic fields that change direction quickly rejoin in pair-dominated outflows. This could speed up particles to PeV energies before termination shocks slow them down. Similar processes in blazar jets could explain why gamma-ray flares change quickly over very short periods of time, even though they come from supermassive black holes that are light years away. Quark-gluon plasma epoch remnants. If you wind the cosmic clock back to the first millionths of a second after the Big Bang, you reach a time before protons, neutrons, or atoms existed. The universe then was filled with quark-gluon plasma, or QGP, a strange state of matter where quarks and gluons, the building blocks of protons and neutrons, moved freely in a hot, dense soup instead of being locked together inside particles. At temperatures above about 2 trillion kelvins, equivalent to particle energies of 150 to 200 mega-electron volts, the strong nuclear force weakens enough that confinement breaks down, and quarks are no longer bound. For a brief window, from about 10 to the minus 6 to 10 to the minus 5 seconds after the Big Bang, this plasma dominated the universe. As space expanded and cooled, quarks became trapped again, forming protons, neutrons, and eventually the atomic nuclei that everything else is built from. Studying this era matters because the freezing of quarks and gluons into hadrons shaped almost everything we see today: stars, planets, chemistry, and life itself. The details of that phase transition influenced the balance between matter and antimatter, the relic abundances of dark matter and neutrinos, and the tiny density ripples that gravity later amplified into galaxies and clusters. Physicists use particle accelerators to make tiny drops of quark-gluon plasma again. Heavy ions like gold and lead are smashed together at almost the speed of light at CERN's Large Hadron Collider and Brookhaven's Relativistic Heavy Ion Collider. When these crashes happen, they quickly raise the temperature of nuclear matter above 2 trillion kelvins. This creates fireballs that are about 10 femtometers across, which is smaller than an atom, and last for only yoctoseconds, which is 10 to the minus 24 seconds. As the plasma cools and condenses back into hadrons, monitors pick up thousands of particles shooting outward. This gives scientists a look into what the universe was like in its very first microseconds. It's surprising that QGP doesn't behave more like a barely interacting gas, but more like a nearly perfect fluid with very low viscosity compared to entropy density. Instead of particles flying apart, the plasma moves as a group, showing circular flow patterns that show strong interactions between quarks and gluons, even when they are not confined. Its viscosity is getting close to a lower bound that was guessed from string theory's ADS-CFT correspondence. This connects quark-gluon physics to black hole boundaries in spacetimes with more dimensions, which is a surprising link between nuclear physics and quantum gravity ideas. The early universe QGP likely filled all of space, not tiny droplets, so its expansion followed relativistic hydrodynamics rather than isolated fireball explosions. As the universe cooled below 2 trillion kelvins, quarks bound into protons and neutrons, while gluons became confined inside hadrons, locking away color charge permanently. Whether this transition was a smooth crossover or a first-order phase transition with latent heat and bubble nucleation remains debated. Lattice QCD calculations at zero baryon density suggest a crossover at physical quark masses, but conditions with higher baryon chemical potential, relevant to neutron star mergers or cosmic regions with matter-antimatter asymmetries, might feature critical points or first-order transitions, leaving observable relics. What remnants could survive from this epoch? One possibility involves quark nuggets or strangelets, macroscopic chunks of strange quark matter stable against decay into ordinary nuclei. If the quark-hadron transition proceeded through bubble nucleation, shrinking QGP regions might have cooled into dense quark matter nuggets before converting fully to hadrons. Searches for strangelets in cosmic rays, lunar soil, or collider experiments have so far found nothing conclusive, placing upper limits on their abundance. But neutron star cores, with densities above nuclear levels, might still harbor strange quark matter today if it forms the true ground state of dense baryonic matter. In that case, collisions of compact stars could eject strangelets into space, where detectors like AMS-02 aboard the International Space Station might someday spot them among cosmic ray fluxes. Another way to look is with gravitational waves. First-order quark-hadron transitions with bubble collisions, turbulence, or sound waves in the early plasma would have created random gravity wave backgrounds that future telescopes like LISA or pulsar timing arrays might be able to pick up. So far, no such signs have been seen, but as sensors get better, they might one day show direct evidence of early universe phase changes through space-time ripples. Even though there were no leftover particles or gravitational waves during the QGP era, it set the stage for the Big Bang nucleosynthesis, BBBN, which happened minutes later. The amount of baryons to photons, neutrinos, and the difference between matter and antimatter that survives QGP freeze-out determine the starting conditions for the formation of light elements. By matching the amounts of helium, deuterium, and lithium that have been found, we can indirectly limit the physics of the QGP era. However, we still don't know how baryogenesis might have happened during or before this time. Electroweak symmetry breaking frontiers. Before the universe cooled enough for even quark-gluon plasma, it passed through an even stranger stage, the breaking of electroweak symmetry. At temperatures above about 100 giga-electronvolts, a trillion times hotter than the Sun's core, the electromagnetic force and the weak nuclear force were not separate. They merged into a single unified electroweak force, as described by the Standard Model. In that era, photons, W and Z bosons, the Higgs field, quarks and leptons were all massless, interacting under one perfectly symmetric framework. Space itself carried this symmetry. No particle had intrinsic mass because the Higgs field's value was still zero everywhere. As the universe expanded and cooled around 10 to the minus 12 seconds after the Big Bang, the Higgs field's energy landscape shifted. Its symmetric configuration, balanced at the origin like a ball on a hilltop, became unstable. The field rolled down into a new state with a non-zero value, breaking the symmetry. This spontaneous symmetry breaking gave mass to the W and Z bosons through the Higgs mechanism, while photons remained massless. At that moment, electromagnetism split away from the weak force, fixing in place the particle masses we see today. Mathematically, the Higgs field's vacuum expectation value, written as V equals 246 giga-electronvolts, sets the mass scale for particles. The W boson mass is given by m sub W equals G times V divided by 2. The Z boson mass is given by m sub Z equals the square root of G squared plus G prime squared times V divided by 2, where G and G prime are the electroweak coupling constants. Fermion masses come from their Yukawa couplings multiplied by V, explaining why different particles end up with different masses even though they share the same Higgs background. But the electroweak shift might be more important to the universe than just making mass. If this change was first order instead of a smooth crossing, broken symmetry phase, bubbles would have formed in the symmetric background. These bubbles would have grown, crashed into each other, and released latent heat like water boiling into steam. These kinds of violent dynamics could create random gravitational waves through bubble wall collisions and turbulence, leaving behind tiny signs that future interferometers in space like LISA might be able to pick up. A strongly first-order transition could enable electroweak baryogenesis, a mechanism to explain why matter vastly outweighs antimatter today. As bubbles of broken phase expanded, CP-violating interactions near bubble walls could bias reactions producing baryons over antibaryons. Out of equilibrium conditions, plus baryon number violation from electroweak sphalerons, might then freeze in a net baryon asymmetry once the transition completed. Within the Standard Model, using the measured Higgs boson mass of 125 GeV, the electroweak transition appears to be a smooth crossover, not strong enough to support baryogenesis or gravitational wave production. This drives searches for new physics, extended Higgs sectors, supersymmetry, singlet scalars, that could strengthen the transition, making it first order at higher energies while staying consistent with collider experiments and cosmological constraints. Experiments already probe electroweak symmetry breaking at multiple levels. The Large Hadron Collider, LHC, confirmed the Higgs boson in 2012, measuring its couplings, spin and parity. But whether additional Higgs-like states exist remains open. Precision electroweak measurements from LEP, SLC, Tevatron and LHC test radiative corrections sensitive to undiscovered particles influencing symmetry breaking indirectly. Future colliders, like the proposed International Linear Collider, ILC, or Future Circular Collider, FCC, aim to measure Higgs self-couplings precisely enough to reconstruct its potential shape, clarifying whether new physics modified the early universe electroweak transition. Electroweak sphalerons, which are non-perturbative field forms that break the baryon plus lepton number B plus L rule, are still very important to models of baryogenesis. At high temperatures before symmetry breaks, sphaleron transitions happen a lot, wiping out any B plus L asymmetry that was there before unless it is protected by preserved quantities like the BL number, baryon minus lepton number. This connects electroweak physics to the creation of neutrino mass through leptogenesis. Heavy Majorana neutrinos that break apart could first create a lepton asymmetry, which would then be changed by sphalerons into a baryon asymmetry before they freeze out after the electroweak transition. Another big question is vacuum stability. If we take the standard model of particle physics and extend its equations to very high energies, the math suggests the Higgs potential may actually turn negative at scales between 10 to the 10th and 10 to the 12th giga electron volts. That would mean our current electroweak vacuum is not perfectly stable, but only metastable, a long-lived state that could, in theory, decay to a lower energy phase. Such a decay would happen through quantum tunneling, creating a bubble of true vacuum that expands at the speed of light. Fortunately, the predicted lifetime is far longer than the age of the universe, so the risk is only theoretical. Still, this raises deep questions. Physics beyond the standard model, such as extra-scalar fields or new fundamental interactions, could stabilize the Higgs potential completely or change how it behaves at high energies. Either way, vacuum stability remains one of the frontiers pointing us toward new physics. Breaking electroweak symmetry is connected to studies for dark matter as well. Many models that go beyond the Higgs sector create new scalar or fermionic states that are stable under discrete symmetries. These states naturally behave like dark matter. Their interactions with Higgs fields change both collider signals and the processes that set relic levels during the early universe's freeze-out. Xenont and LZ are direct detection studies that look for Higgs portal dark matter scattering off of nuclei. Indirect searches, on the other hand, look for annihilation signs in cosmic rays or gamma rays. Grand unification phase transition relics. At energies above about 10 to the 16th giga electron volts, far beyond anything we could ever reach in a collider, many theories predict that the three forces of the standard model, the strong, weak, and electromagnetic forces, all merge into a single unified force. These ideas are called Grand Unified Theories, or GUTS. They appeared in the late 1970s and early 1980s to explain things like why electric charge comes in precise units, how quarks and leptons are organized into families, and why the strengths of the forces seem to converge when extended to ultra-high energies. If the early universe really went through a gut phase, cosmic cooling would have broken this unified force apart into the distinct forces we see today. Each of these symmetry-breaking transitions could have left behind relics, strange particles, topological defects, or even cosmological signatures, offering us indirect evidence of physics at energies otherwise completely out of reach. One famous relic is the magnetic monopole. In GUT models, when the unified group breaks into subgroups that include U1, the symmetry of electromagnetism, topological arguments almost always predict monopoles, point-like particles carrying net magnetic charge. They would be extremely massive, on the order of 10 to the 16th giga electron volts or more, and stable, making them long-lived fossils from the universe's first instance. Early calculations suggested monopoles should have been so common that their combined mass would outweigh the entire universe, clearly contradicting observations. The solution came with cosmic inflation. If inflation occurred after monopoles formed, it would have stretched space so fast that their density was diluted to almost nothing. This explains why, despite decades of searching in cosmic rays, lunar samples, and dedicated detectors like Moidal at the Large Hadron Collider, no magnetic monopoles have ever been found. The first models of cosmic strings projected changes in density that were too big to match the cosmic microwave background, CMB. This meant that they couldn't be used as primary structure seeds, but they are still a strong candidate for gravitational wave sources. Gravitational waves are sent out by oscillating string loops over a very wide frequency range. Pulsar timing arrays, ground-based interferometers like LIGO, or future space-based detectors like LISA might be able to pick them up. Recent hints of a random gravitational wave background in pulsar timing data from Nanograv and similar projects have even sparked new interest in cosmic strings as possible sources, along with astrophysical or early universe inflationary ones. Gut transitions might also produce domain walls, two-dimensional defects separating regions where fields settle into different vacuum states. However, stable domain walls would quickly dominate cosmic energy density as the universe expands, conflicting with observations. This domain wall problem constrains viable symmetry-breaking patterns. Either inflation dilutes walls away, or models avoid discrete symmetries producing stable walls altogether. Relic X-particles, supermassive gauge or Higgs bosons mediating proton decay in GUTs, could also leave imprints if they decayed out of equilibrium after inflation, producing baryon asymmetry through CP-violating, baryon number-violating interactions. This mechanism, known as Gutti baryogenesis, links matter-antimatter asymmetry to physics at unimaginable energies, though later developments like Electroweak sphalerons and leptogenesis complicate the picture by erasing or converting asymmetries, depending on conserved quantum numbers. Some models connect changes in the gut scale to inflation itself. In hybrid inflation, for example, a scalar inflation field causes exponential growth until it reaches a critical number. This breaks the gut symmetry and ends inflation through a process known as waterfall transition. In these cases, reheating after inflation fills the universe with particles, radiation, and maybe even cosmic strings or gravity waves that carry clear signs of the high-energy physics that lie beneath. Gravitational wave astronomy offers complementary probes. A first-order gut phase transition would produce stochastic gravitational wave backgrounds from bubble collisions, turbulence, or sound waves in the primordial plasma. Frequencies depend on transition temperatures and expansion dynamics, often peaking far above LISA's millihertz band, but potentially within reach of cosmic microwave background polarization experiments or high-frequency gravitational wave detectors under development. Cosmic magnetic fields might also trace their origin to gut transitions. Phase boundaries and defects could seed primordial fields later amplified by galactic dynamos, leaving imprints in intergalactic voids or CMB anisotropies. Observations of Blazer halos and Faraday rotation in distant quasars already hint at femtoGauss-level fields across megaparsec scales, though whether these arose during GUT, Electroweak, or inflationary epochs remains open. Primordial Planck mass black hole relics. In the first split second after the Big Bang, space wasn't calm. It was full of tiny ripples, some regions a bit denser than others. If a spot was just dense enough, gravity could crush it into a black hole right away. These are called primordial black holes, and unlike normal black holes that form when stars die, these ones were born straight out of the early universe itself. What's strange is that they could come in all sizes. Some heavier than stars, some lighter than asteroids. And at the tiniest extreme, some could shrink all the way down toward the Planck mass, about 20 micrograms, lighter than a grain of dust. Stephen Hawking showed that black holes aren't eternal. They slowly leak energy, called Hawking radiation, and the smaller they are, the faster they evaporate. A big black hole like the ones in space today barely changes, but a tiny one burns energy like crazy until, in theory, it disappears. Now, if a primordial black hole started with the right mass, it could have been evaporating for the entire history of the universe, only finishing right about now. Lighter ones should have already vanished. What happens when they get so small that they're near the Planck mass? That's where our math breaks. Some scientists think the evaporation may stop there, leaving behind a tiny stable relic, a frozen nugget of pure quantum gravity. These relics could still be floating around today, and some even think they might make up dark matter. Alternatively, first-order cosmological phase transitions, like the QCD or Electroweak transitions, could concentrate energy into bubbles, cosmic strings, or domain walls, whose collisions form PBHs across a mass spectrum. If evaporation leaves relics, each event seeds a stable Planck-scale object persisting indefinitely. Such relics could behave as a form of cold dark matter. Their masses lie far below astrophysical detection thresholds. Yet their cosmic abundance could match observed dark matter densities if enough PBH is formed before inflation diluted or after reheating repopulated them. Unlike particle dark matter candidates like WIMPs or Axions, PBH relics would arise from gravity itself, requiring no new fields beyond quantum gravity corrections, halting evaporation. So what could actually stop a tiny black hole from vanishing completely? Scientists have a few ideas. A potential theory is that quantum gravity makes it impossible for things to be too big. In some models, space has a minimum length scale. What this means is that a black hole can't get any smaller than about the Planck length. When the evaporation stops, a steady residue is left behind. Another thought comes from the study of strings. When their mass is very small, black holes can change into strange stringy things that are sometimes called string balls or brain remains. These would be very stable and last a lot longer than regular black holes, and in loop quantum gravity, the inside of a black hole doesn't end in a singularity at all. Instead, space might rebound in a kind of quantum bounce. In this view, a black hole could tunnel into a tiny white hole, freezing as a leftover relic just above the Planck scale. In all of these scenarios, the same theme appears. Instead of disappearing, the black hole leaves behind a Planck-sized fossil of the early universe. Observationally, PBH relics remain elusive because their tiny masses and sizes produce no detectable Hawking radiation today if evaporation already ceased. They interact only gravitationally unless carrying exotic charges, making direct detection nearly impossible with current technology. Still, indirect constraints arise. If PBHs evaporated entirely, their final gamma-ray bursts would contribute to the diffuse gamma-ray background. Lack of excess signals limits initial PBH abundances across mass ranges. But if evaporation halts early, relics avoid these constraints, hiding as cold dark matter candidates clustering in galactic halos, or even forming Planck star cores inside larger black holes. Some theories speculate about relics storing information otherwise lost in black hole evaporation, offering potential resolutions to the black hole information paradox. If relics retain quantum correlations from their formation, they might preserve unitarity despite Hawking radiation's apparent thermal nature, though critics argue relic scenarios require implausibly vast information densities in Planck-sized volumes. Spacetime foam residue structures. At the Planck scale, about 10 to the minus 35 meters, our usual view of space as smooth and continuous breaks down. Quantum mechanics says that everything fluctuates at small enough scales, and since gravity is tied directly to energy, those fluctuations cause spacetime itself to writhe and twist. In this regime, spacetime may churn like a storm, bending, stretching, and even tearing faster than light can cross the region. Physicist John Wheeler called this chaotic state spacetime foam, a frothy ocean of tiny wormholes, bubbles, and fleeting structures that pop in and out of existence. While Einstein's general relativity treats spacetime as a smooth fabric shaped by mass and energy, the uncertainty principle tells us that confining energy below the Planck length creates fluctuations so intense that space itself may briefly sprout baby universes, open wormholes, or shift its shape entirely, only to collapse back into the quantum vacuum. If this spacetime foam filled the early universe, some relic structures might survive cosmic expansion, inflation, or phase transitions, leaving permanent though minuscule imprints on the cosmos. These spacetime foam residues could appear as microscopic wormholes, Planck-scale black holes, or defects carrying exotic quantum numbers like magnetic charge or baryon number, trapped when quantum geometry froze into classical spacetime as the universe cooled. Some quantum gravity models even predict specific relics. In Euclidean quantum gravity, spacetime histories sum over all possible geometries, including topologically non-trivial ones with wormholes connecting distant regions. Certain wormholes, once formed, might freeze if cosmic expansion stretches them beyond quantum fluctuation scales, becoming permanent microscopic tunnels threading spacetime. In loop quantum gravity, spacetime geometry itself emerges from spin networks, discrete graphs carrying quantized areas and volumes. Quantum transitions between spin network states at the Planck scale could leave behind regions where topology differs from surrounding space, forming relic defects analogous to crystal dislocations in condensed matter systems. String theory offers yet another perspective. Extra dimensions compactified on Calabi-Yau manifolds might host topological cycles where fluxes or branes wrap non-trivial surfaces. Quantum fluctuations could nucleate brane-antibrane pairs, tiny handles, or orbifold singularities, some of which might persist as stable Planck-scale remnants if no decay channel exists. Could these relics be found? It looks like direct observation won't work. Structures on the Planck scale are 20 times smaller than atomic atoms. But effects that build up over vast distances or time might show secondary signs. For example, tiny wormholes or changes in the shape could make global symmetries look like they aren't being followed by letting charge or baryon number leak through secret dimensions. Some big theories already say that baryon numbers will be violated. Spacetime foam could make this happen even more, which could change the rates at which protons break down or the early stages of baryogenesis. Lorentz invariance violation, LIV, is another option. If spacetime foam changes the way photons or neutrinos move on very small scales, then high-energy objects moving billions of light-years may show changes in speed that depend on their energy. Gamma-ray burst photons with different strengths could be sent out at the same time and arrive at Earth with small delays due to the vast distances between galaxies. Such effects are already tightly limited by telescopes like Fermi-Leyte and MAGIC. As of now, there is no strong proof for LIV, which would push quantum gravity scales close to or above Planck energy. Spacetime foam might also scatter or decohere quantum states passing through it, producing minute fuzziness in interference patterns from distant astrophysical sources. Future instruments measuring coherence of light from quasars or gravitational waves from merging black holes could test such effects statistically, though separating them from ordinary astrophysical noise remains challenging. Some theorists speculate about holographic noise, random fluctuations in spacetime positions, predicted if spacetime information density obeys holographic bounds. Interferometers like GEO 600 and proposed experiments such as the holometer aim to detect this noise as correlated jitter in optical paths, though results so far remain inconclusive. If relic wormholes or defects persist, they might even contribute to dark matter, Planck mass remnants, microscopic black holes, or stable topological defects could cluster gravitationally without interacting electromagnetically, behaving as cold dark matter on large scales while remaining invisible to conventional searches. Their formation rates would depend on unknown quantum gravity dynamics during the Planck epoch, inflation, or subsequent phase transitions. Analogues from the lab are also useful. Some condensed matter systems like superfluid helium or Bose-Einstein condensates show new spacetime shapes with topological flaws, boundaries, and quantum turbulence that look like spacetime foam at sizes that we can see. Studies of flaw formation, quantum swirls, or analog Hawking radiation give us a good idea of how the structure of spacetime at the microscopic level might change during phase transitions or quantum fluctuations. Extra-dimensional leakage regions. In everyday physics, spacetime looks four-dimensional, 3 dimensions of space and 1 of time, all described by Einstein's general relativity. But many theories that go beyond the standard model, like string theory and brane-world cosmology, suggest there could be extra dimensions curled up so tightly we can't see them. If these hidden dimensions exist, they might let particles, forces, or even gravity slip out of our familiar world under extreme conditions, breaking rules we normally consider unshakable, like the conservation of energy or the inverse square law of gravity. In string theory, 6 or 7 extra dimensions are thought to be compactified into tiny Calabi-Yau shapes at scales near the Planck length, about 10 to the minus 35 meters. The particles we know, quarks, electrons, photons, are vibrations of strings confined to a 3-dimensional brane, while gravity may roam freely through the higher dimensional bulk. That freedom could explain why gravity seems so weak compared to other forces. its field lines spread into hidden dimensions, thinning out in ways we can't yet measure. This idea underlies brain-world models like those of Arkani Hamid Dimopoulos Dvali, ADD, and Randall Sundram, RS. In ADD, large extra dimensions, perhaps as big as fractions of a millimeter, lower the fundamental Planck scale to the TV range, making quantum gravity potentially accessible at colliders or in cosmology. RS models, with warped rather than flat extra dimensions, localize gravity near our brain while allowing exponentially large hierarchies between physical scales across the bulk. What would leakage into extra dimensions mean physically? In particle collisions above the true fundamental gravity scale, energy might produce Kaluza-Klein gravitons, tower-like excitations corresponding to graviton momentum modes along compact dimensions, escaping into the bulk and carrying energy invisible to detectors. Missing energy signatures at the Large Hadron Collider, LHC, already constrain such scenarios, though no confirmed signals have appeared. If extra dimensions open up at high energies, the early universe might send gravitational degrees of freedom into the rest of the universe. This could change the rate of expansion, the results of nucleosynthesis, or the cosmic microwave background, CMB, anisotropies. Because of this, accurate measurements of the amounts of light elements and CMB sound peaks limit how easily energy could escape from our brain and enter higher dimensions after the Big Bang. Black holes offer another extreme test. In higher dimensions, gravity doesn't weaken with distance the way we're used to. Normally, Newton's law says gravity falls off as 1 divided by distance squared. But if there are extra dimensions, the rule changes. Gravity would fall off as 1 divided by distance to the power of n plus 1, where n is the number of hidden dimensions. That means gravity could become much stronger at very short ranges. If the true Planck scale were near the tera-electron-volt range, as once hoped for at the Large Hadron Collider, then particle collisions could have been powerful enough to create tiny black holes. These microscopic black holes would quickly evaporate through Hawking radiation, spraying out many particles at once, or perhaps shrinking only down to stable Planck mass remnants if evaporation stops at the quantum gravity scale. But since no such events have been detected, experiments have already ruled out many scenarios where the fundamental scale sits just a few tera-electron volts above everyday physics. Astrophysics offers complementary tests. If gravitons propagate in the bulk, gravitational waves from merging neutron stars or black holes might lose energy into extra dimensions, altering observed waveforms. LIGO-Virgo observations already constrain such losses because detected signals match four-dimensional predictions closely. Likewise, cooling rates of supernovae like SN 1987 limit exotic channels. If too much energy leaked into bulk gravitons or sterile neutrinos, observed neutrino bursts would have shortened dramatically. Some models even allow standard model particles to tunnel into hidden branes under extreme fields or densities. In scenarios with mirror branes carrying duplicate particle sectors coupled only gravitationally or through faint kinetic mixing, neutrons in intense magnetic traps might oscillate into mirror neutrons, disappearing from our brain before reappearing. Experiments search for anomalous neutron losses or regeneration events constraining such exotic mixings, though results so far show no deviations from standard physics. At the highest energies, near the fundamental Planck scale, spacetime itself might fluctuate between topologies connecting multiple branes or dimensions through microscopic wormholes. Particles or charges could leak through these quantum gravitational shortcuts, violating global symmetries like baryon or lepton number. Some baryogenesis models exploit such effects, letting asymmetries form through interactions inaccessible in purely four-dimensional settings. Virtual effects from other dimensions could change precise observables in small ways, even if there isn't direct loss. Running coupling constants, Higgs potentials, or Electroweak precision factors can be changed by Kaluza-Klein modes. In the future, colliders that measure Higgs self-couplings, top quark features, or rare decays might find heavy extra-dimensional states in a roundabout way, even though they can't be made directly. Holographic boundary emergent zones. In classical physics, space feels fundamental, We imagine particles moving through a three-dimensional stage with time ticking uniformly everywhere, while gravity curves this stage without erasing its underlying continuity. But a radical idea born from black hole thermodynamics and string theory suggests spacetime itself might be holographic, that the three-dimensional universe we experience emerges from information stored on a lower dimensional boundary, much like a 3D hologram projected from a 2D surface. This idea goes back to Jacob Bekenstein and Stephen Hawking, who showed in the 1970s that black holes carry entropy. But unlike ordinary systems, their entropy doesn't scale with volume, it scales with surface area. The formula is entropy equals Boltzmann's constant times the speed of light cubed times the horizon area divided by 4 times Newton's constant times Planck's constant. In simpler words, the bigger the surface of the black hole, the more information it holds. This surprising rule suggests that the maximum information inside any region of space isn't determined by its volume, but by the area of its boundary. In the 1990s, Gerard 't Hooft and Leonard Susskind generalized this insight into the holographic principle. The physics within any volume of spacetime might be fully described by degrees of freedom living on its boundary, with 1 bit per Planck area setting the ultimate information density. Our familiar 3D bulk reality could thus emerge from a 2D quantum theory at the boundary, erasing the distinction between interior and exterior fundamentally. String theory sharpened this idea through the ADS-CFT correspondence, discovered by Juan Maldacena in 1997. In this duality, a gravity theory in D+1 dimensional anti-de Sitter ADS space exactly equals a conformal field theory CFT without gravity living on its d-dimensional boundary. Black holes in the bulk map to thermal states in the boundary CFT, bulk particles map to boundary operators, bulk spacetime geometry itself emerges from quantum entanglement patterns in the boundary theory. Even though our universe isn't ADS because of de Sitter-like geometry and cosmic acceleration, ADS-CFT gives us clear, measurable models for how spacetime forms holographically from lower dimensional physics. As an example, the Ryu-Takayanagi formula connects the entanglement entropy in the border CFT to the smallest surface areas in the bulk ADS geometry. This makes the connection between quantum information and the curve of spacetime in the classical sense. If holography is what reality is made of, then the edges of things like black holes, the edges of the universe, and Rindler horizons that are close to viewers moving very quickly might be holographic emergence zones where mass locality breaks down into border quantum degrees of freedom. It's not possible for bulk effective field theory to work near these borders because Hawking radiation, entropy limits, and unitarity demands force quantum gravity to store bulk information on boundary surfaces in a way that isn't local. Experiment signs are still hard to find but interesting. The Bekenstein bound limits entropy and therefore information inside areas with set size and energy. So far, no system has been able to go beyond this bound, which is in line with what hologram theory says should happen. Raphael Bousso came up with the idea of the covariant entropy bound, which applies this to any light sheet. This means that holography limits all parts of spacetime, not just black holes. Our universe's cosmological horizon from accelerated expansion resembles a de Sitter horizon with finite entropy proportional to its area. If holography applies, the observable universe's information content might live on this cosmic horizon, with bulk spacetime and matter emerging from boundary quantum degrees of freedom we cannot directly access. Some even speculate cosmic time itself could emerge from boundary entanglement dynamics, as bulk radial coordinates in ADS emerge from renormalization group flow in boundary theories. High-energy collisions offer other tests. If bulk spacetime obeys holographic bounds, attempts to pack energy into volumes above certain thresholds should create black holes rather than arbitrarily small structures, preventing information densities above 1 bit per Planck area. This aligns with expectations from string theory's string black hole correspondence, where highly excited strings and small black holes become indistinguishable near the Planck scale. Quantum information theory now drives much holography research. Tensor network models like Mirror, multiscale entanglement renormalization ansatz, reproduce ADS-like geometries from entanglement patterns, hinting spacetime connectivity equals quantum entanglement structure. The slogan ER=EPR, proposed by Maldacena and Susskind, even links Einstein-Rosen ER bridges, wormholes, to quantum entanglement EPR pairs, suggesting spacetime geometry arises from quantum correlations themselves. Some search for holographic noise, Planck-scale positional uncertainty from limited information density, using interferometers like the Fermilab holometer. Results so far show no confirmed deviations from classical spacetime smoothness, pushing any holographic discreteness below current sensitivity. Gravitational wave detectors might someday test holographic correlations in spacetime fluctuations if signals accumulate over cosmic distances. In a roundabout way, astrophysical data could also limit holography. If inflationary changes fill up the holographic entropy limits, the cosmic microwave background, CMB data, might hold clues about the holographic starting conditions, but there isn't yet a smoking gun. No matter what, holography fixes long-standing problems like black hole information loss. If bulk interior physics comes from boundary degrees of freedom evolving unitarily, then information never goes away behind horizons, even though this goes against bulk, semi-classical perception. The whole thing, even parts inside black holes, would be a quantum projection from boundary dynamics that clearly keeps unitarity. Quantum chaos, horizon scrambling regions. Not only do black holes bend spacetime and eat matter, they also scramble data so quickly that they reach the limits of quantum mechanics. Because of this, they are very important for understanding quantum chaos, which is the study of how differences in quantum systems that start out very small get bigger and bigger over time, making it hard to predict what will happen and spreading information across degrees of freedom. This scrambling gets to levels that have never been seen before in physics near the borders of black holes. It connects thermodynamics, quantum information, and gravity in ways that hint at the basic ideas behind spacetime itself. The story begins with black hole thermodynamics. Hawking radiation makes black holes thermal objects with entropy proportional to horizon area and temperature inversely proportional to mass. Yet thermodynamic systems mix information slowly compared to black holes. In quantum many-body physics, scrambling measures how quickly local quantum information spreads across a system's degrees of freedom until it hides in global correlations inaccessible to local observers. Black holes seem to be the fastest scramblers of information in the universe. In 2016, Maldacena, Schenker, and Stanford discovered a bound on how quickly chaos can grow in a quantum system. The rule says the Lyapunov exponent, basically a measure of how fast small changes blow up, can be no greater than 2 pi times Boltzmann's constant times temperature, divided by Planck's constant. Black holes actually saturate this bound, meaning they scramble information as fast as the laws of physics allow. If you drop a single qubit of information into a black hole within a short scrambling time, roughly 1/2p times the temperature, multiplied by the logarithm of the entropy, that information gets spread out across the entire horizon. It becomes so mixed that no small piece of Hawking radiation carries it alone. Only the full set of correlations across all the radiation contains the hidden record. This connects directly to the black hole information paradox. Hawking's semi-classical calculation implies radiation emerges thermally, carrying no information about what fell in. But if black holes behave as unitary quantum systems scrambling information maximally before re-emitting it in correlations among outgoing quanta, the paradox softens. Information isn't destroyed, only highly scrambled. The Hayden-Preskill protocol models this. Once half the black hole evaporates, new information thrown in emerges quickly after only short delays, encoded in subtle correlations, possible because black holes scramble so efficiently. Holography makes these connections stronger. Black holes in the bulk of ADS CFT are the same as temperature states in the border conformal field theory CFT. OTOCs measure quantum chaos at the boundary, which is related to the behavior of mass gravity, shock waves close to the horizons. So, scrambling can be described in 2 ways. as chaotic quantum information spreading in the CFT, and as gravitational interactions near the edges of black holes in the bulk. Even gravitational shock waves themselves reveal chaos. In near-horizon geometries, tiny perturbations shift in falling trajectories exponentially, like classical chaos sensitivity to initial conditions but realized through spacetime curvature. This exponential growth yields the same Lyapunov exponents governing boundary otoks, uniting chaos, gravity, and quantum information mathematically. Quantum circuits and random unitary dynamics are being looked at as models for black hole scrambling in new research. The Sachdev-Yekitaev SYK model is made up of fermions that interact randomly with each other. It shows maximal chaos and holographic duality to nearly ADS2 black holes. This lets theorists figure out otoks, entropies, and correlation functions analytically in fast scrambling systems that look like the edges of black holes. There are now signs of quantum shifting being tested in labs. We can make trapped ion systems, superconducting qubits, and ultra-cold atoms work like otoks by partly undoing time evolution and finding information spreading in man-made many-body systems. Even though these studies aren't very close to real black holes, they do test mathematical tools that link chaos limits, thermalization, and entanglement growth in a controlled setting. Astrophysically, quantum chaos near horizons might influence gravitational wave signals from black hole mergers. If near-horizon quantum structures modify scrambling or information retention, ring-down phases following mergers could carry subtle imprints beyond classical general relativity's predictions. Future detectors like LISA or third-generation ground observatories might probe such effects through high-precision waveform analysis. De Sitter horizons in universes that are expanding faster have the same thermodynamic qualities as black hole horizons. They have entropy that is proportional to the size of the horizon and temperature that is proportional to the gravity at the surface. If quantum chaos and scrambling reach the cosmological horizons, the visible universe may scramble quantum information the most. This would make a conceptual link between inflationary effects, cosmic microwave background correlations, and horizon thermodynamics. The ER=EPR conjecture ties chaos, entanglement, and spacetime geometry even deeper. If wormholes, Einstein-Rosen bridges, connect entangled black holes, Einstein-Podolsky-Rosen pairs, then scrambling quantum information across entangled horizons might literally stretch or shape spacetime wormholes dynamically. Quantum teleportation protocols through holographic wormholes already simulate such ideas in toy models using SIK dynamics, merging quantum chaos, gravity, and quantum information experimentally at tabletop scales. Fast scrambling also has links to page curves that show how black holes' entropy changes over time. In the beginning, Hawking radiation entropy increases thermally, but after the page time, when half of the black hole disappears, unitarity demands that entropy decrease as information escapes through correlations between radiation quanta. Holography's quantum extremal surface calculations can now accurately recreate page curves. This shows how scrambling, entanglement wedges, and copy wormholes work together to keep information safe while matching semi-classical gravity at intermediate times. Firewall and fuzzball horizon transition zones. Even though black holes have always been weird, a paradox in 2012 made them even stranger. The AMPS conundrum, named after Almhiri, Marolf, Polchinski, and Sully, said that if information is kept when a black hole evaporates, then something must change a lot at the event horizon. The horizon might not behave as expected by general relativity. Instead, it could turn into a fiery firewall of high-energy particles that destroy anything falling through it. This would break Einstein's equivalence principle, which says that physics near horizons should feel the same as free fall in empty space. The reasoning begins with Hawking radiation. In Hawking's calculation, particle-antiparticle pairs form near the horizon. One escapes as radiation, while the other falls inward, entangled with its partner. As evaporation continues, outgoing radiation accumulates correlations with earlier radiation to preserve unitarity, but each new quantum also remains entangled with its interior partner unless something breaks. Quantum mechanics forbids a single system from being maximally entangled with two independent systems simultaneously. This is monogamy of entanglement. After the page time, when radiation entropy begins decreasing, interior-exterior entanglement must break somehow. The AMPS team argued this break forces violent consequences. Without smooth entanglement across the horizon, quantum fields there can't stay in the vacuum state freefall observers expect. Instead, high-energy excitations would appear, forming a firewall, incinerating anything crossing the horizon. Unitarity, quantum field theory, and general relativity can't all survive together. One principle must give. Many physicists dislike firewalls because they violate the equivalence principle, a central pillar of general relativity. Alternatives emerged quickly. One major proposal is the fuzzball concept from string theory. Here, black holes have no traditional interior at all. Instead, each microstate corresponds to a horizon-sized quantum fuzzball configuration of strings and branes. There's no empty space behind a horizon, so infalling observers encounter structure, stringy degrees of freedom, not smooth spacetime. Hawking radiation simply comes from these microstate surfaces directly, preserving unitarity without needing interior partners or firewalls, appearing suddenly midway through evaporation. Fuzzballs replace singularities and horizons with quantum geometry extending across what classical gravity calls the interior. Each microstate looks different microscopically, but averages macroscopically to familiar black hole thermodynamics, explaining entropy as counting distinct fuzzball states, rather than coarse-graining over smooth interiors. Radiation then emerges in pure states, carrying information about the specific fuzzball microstate, rather than featureless thermal quanta, resolving the information paradox without firewalls forming abruptly after the page time. Holography and quantum extremal surfaces add more nuance. Calculations of page curves in AD-CFT using replica wormholes show Hawking radiation entropy follows unitarity exactly without requiring firewalls at late times. Quantum extremal surfaces jump after the page time, effectively encoding black hole interiors within the entanglement wedge of outgoing radiation. From this viewpoint, no drama hits infalling observers. Horizons stay smooth, but quantum information flows out through subtle correlations, encoded non-locally by holographic duality. Others think there might be solid Planck mass things left over after evaporation stops. Remnants could keep all information without firewalls, fuzzballs, or wormholes. But critics say that this would require ridiculously high information densities in very small amounts, which would create even more problems than the ones that came before. Planckian scattering breakdown regions. All the way from the electron-volt sizes of atoms to the tera-electron-volt collisions of the Large Hadron Collider, physics works just fine. For example, our known frames don't work at Planck energy, which is about 1019 giga-electron-volts, or about 35 meters away. In quantum field theory, spacetime is thought to be flat, but in general relativity, curvature is seen as a pure classical phenomenon. When you look at things on the Planck scale, both pictures fall apart. Gravity becomes as strong as the other forces. Spacetime shakily changes shape, and concepts like distance, time, and cause and effect may disappear. Normally, higher energy collisions let us see smaller structures. Giga-electron-volt electrons uncovered atomic nuclei, and tera-electron-volt protons revealed quarks and gluons. By that logic, Planck energy collisions should expose details at 10 to the minus 35th meters. But gravity blocks the path. At around 10 to the 19th giga-electron-volts, concentrating energy into such tiny regions would not reveal finer structure. It would form black holes. Instead of exposing sub-Planckian spacetime, the collision collapses into a horizon, hiding everything inside. To truly explore beyond the Planck scale, we need a complete theory of quantum gravity, not just bigger particle accelerators. Near this limit, familiar scattering amplitudes diverge or lose meaning. Classical general relativity predicts gravitational interactions growing with energy squared. Quantum field theory predicts ultraviolet divergences, requiring renormalization. gravity resists renormalization in 4 dimensions. Adding quantum corrections introduces infinite counterterms without predictive power. Something new: string theory, loop quantum gravity, asymptotic safety, causal dynamical triangulations must tame Planckian scattering where ordinary perturbative methods fail completely. String theory softens collisions naturally because fundamental strings have finite size. At energies above the string scale, strings stretch rather than probe ever smaller distances, replacing point-particle divergences with extended objects spreading interactions across worldsheets. High-energy string scattering amplitudes become finite and even exhibit T-duality. Physics at distances below the string length mirrors physics above it, forbidding resolution beyond a minimal length. Other methods predict changes that are just as big. Spacetime is broken up into spin networks with quantized areas and volumes by loop quantum gravity. Planckian scattering then looks at discrete quantum geometry instead of smooth surfaces. The causal set theory replaces the spacetime continuum with basic causal relationships. Asymptotic safety scenarios say that gravitational links get closer to ultraviolet fixed points, which makes things more predictable without adding any new particles, but drastically changes how things move over short distances. Phenomenologically, Planckian scattering might produce microscopic black holes, wormholes, or spacetime foam rather than ordinary particles. In scenarios with large extra dimensions lowering the fundamental Planck scale to TV energies, as once proposed in Arkani-Hamed-Dimopoulos-Dvali (ADD) models, the Large Hadron Collider could have produced transplanckian objects already. None appeared, pushing fundamental gravity scales far above TV ranges and limiting such exotic possibilities dramatically. UHCRs that hit Earth's atmosphere have center of mass energies above 100 TeV, which is much higher than what colliders can do, but they don't seem to cause any transplanckian effects. If there were tiny black holes, violations of Lorentz symmetry, or quantum gravity cross-sections at these sizes, they might be seen in air shower patterns or neutrino interactions. So far, data from the Pierre Auger Observatory and IceCube are very close to what the standard model says should happen. This rules out a lot of possible Planckian situations. When it comes to math, scattering close to the Planck scale might involve completely new degrees of freedom. Some ideas say that gravitons, which are quantum carriers of gravity, become highly linked above certain energies, which means that they need to go back to black hole states instead of perturbative particles. Others talk about holographic duality. It's possible that Planckian bulk scattering can be linked to non-gravitational interactions in quantum field theories with fewer dimensions by using ADS-CFT and swapping out geometric singularities for well-defined boundary correlators. Entropy bounds also limit Planckian collisions. The Bekenstein-Hawking entropy scaling with horizon area implies maximal information density at 1 bit per Planck area. Collisions above this density form horizons rather than revealing substructure, preventing violations of the covariant entropy bound. Physics beyond the Planck scale thus hides behind holographic screens, inaccessible to local probes, but perhaps describable by dual quantum systems without gravity. Some approaches explore S-matrix unitarity at trans-Planckian energies. String theory's Veneziano amplitudes preserve unitarity automatically, while black hole formation suggests partial wave unitarity saturates through geometric cross-sections rather than perturbative divergences. As energies climb, classical black holes dominate scattering. Hawking radiation then re-emits information slowly, linking unitarity, black hole thermodynamics, and quantum gravity fundamentally. Faint signatures of that physics might still be imprinted in the primordial patterns we see today. The windows through which we can see are still small, but they are beginning to get bigger. Experiments in the future, such as ultra-high energy neutrino detectors, cosmic ray telescopes, and advanced gravitational wave interferometers, might give us a sneak peek into Planck-scale physics. They could pick up very small effects, like small breaks in Lorentz symmetry, small changes in the speed of light based on energy, or strange increases in scattering rates at very high energies. Quantum fluctuations at the Planck scale were spread out across the universe during inflation, which may also hold hints. If quantum gravity changed those changes, we might still be able to see tiny signs of that physics in the patterns we see today. Cosmic singularity quantum bounce regions. At the heart of classical general relativity lurk singularities, regions where densities, curvatures, and energies diverge, and Einstein's equations break down completely. The most famous appear at the Big Bang, where the entire universe emerges from an initial singular point, and inside black holes, where matter collapses beyond any known physical description. These infinities signal not physical reality, but the limits of classical theory. Most physicists believe quantum gravity, merging relativity with quantum mechanics, will replace singularities with finite, well-defined structures, perhaps even bounces where collapse reverses into expansion under extreme quantum effects. Loop quantum gravity suggests that spacetime itself may be made of discrete building blocks at the Planck scale, about 10 to the minus 35th meters. In this view, areas and volumes come in indivisible quanta, so no region of space can shrink to zero size. This prevents the infinite densities predicted by classical general relativity. When these ideas are applied to the whole universe, an approach called loop quantum cosmology, the Big Bang singularity is replaced by a big bounce. As the universe contracts toward Planck-level densities, quantum geometry creates a repulsive effect that counteracts gravity. Collapse halts before reaching infinity, and the universe rebounds into expansion. There are changes made to the Friedmann equations in math. When densities are very high, new terms equal to density squared change the direction of gravity's pull. When the density goes above about 40% of the Planck density, the scale factor stops decreasing at a small but non-zero number, then starts to grow again. Simulations back up this picture, showing that quantum states of geometry can change smoothly during the bounce, acting in a classical way when the curvature is low, but actively resolving singularities when the conditions are very high. Similar things happen when you use other quantum gravity ideas. String theory suggests that the Big Bang in our universe happened because of brane collisions in higher dimensions, during pre-Big Bang stages or ekpyrotic models. The AD-CFT correspondence suggests that bulk singularities might be able to map to well-behaved boundary quantum field dynamics, which would replace infinities with descriptions that are strongly linked but limited. Asymptotically safe gravity says that ultraviolet fixed points can control high-energy divergences, which could make singularities smooth into cores with limited curvature. String theory offers fuzzball models where microstate geometries without horizons, or singularities, replace classical black holes entirely. Instead of bounces, fuzzballs fill interiors with stringy structures, removing smooth spacetime altogether, resolving singularities by eliminating them rather than evolving through them. High-energy cosmic rays or gamma-ray bursts might even probe black hole bounce scenarios. If evaporating black holes tunnel into white holes explosively after long lifetimes, final bursts could produce observable transients. Some fast radio burst (FRB) models speculate about Planck star explosions, though most astrophysicists favor magnetars or compact object mergers for FRB origins currently. Theoretically, bouncing models connect to energy conditions in general relativity. Classical singularity theorems assume conditions like the null energy condition, NEC. Quantum fields can violate NEC locally via Casimir effects or renormalize stress tensors, enabling bounces without contradicting average conditions globally. Understanding such violations consistently requires quantum gravity frameworks, ensuring stability, causality, and unitarity, despite exotic matter or modified dynamics near Planckian densities. Asymptotic safety is used in some plans. This is when gravitational couplings get close to ultraviolet fixed points, which makes high curvature regimes scale invariant instead of unique. At Planckian scales, spacetime near singularities might then show fractal-like structures with effective dimensions going below 4. This would soften divergences geometrically instead of actively bouncing them outward. We've looked into the places where physics starts to break down, like Planck-scale foam, bouncing worlds, and boundaries that mess up information at the quantum level. These are likely to be the sites of the next big scientific breakthroughs. The solutions could change how we think about reality, space, and time. Like, subscribe, and come along with us as we go beyond horizons. If you want to keep exploring the wildest edges of the universe, where every new finding changes the rules in new ways.